What an amazing day today. Today, we are bringing together the whole world on micro LED technology. We are actually working together with EPIC, PIDA, and ISA to bring together the entire supply chain of mini and micro LEDs to make sure that we start new cooperations. I would like to thank so much the amazing work of PIDA and ISA that have done for making this meeting come true. We had people registered for this meeting, more than 200 companies. We did an exercise. We loved it. What we did is for every company that registered today, at least as of last night in Europe, we studied what they do and we built this supply chain. We have selected which companies play the role of end user, which companies are making displays, which companies are making the equipment for the manufacturing of micro LED assemblies, which companies are making micro optics, laser technologies, LEDs, which companies can do the semiconductor production, which can provide the materials for the semiconductor production. We are all mapped here. And the reason that we do this meeting is that for the next 3 hours, we want you to do business. We want you to connect with the right companies. We have this fantastic agenda with companies from all over the world, which all of them have a success story to share with you. I am the co-moderator of this fantastic event. I am the CTO, Chief Technology Observer of EPIC, and I also have the pleasure to co-chair this meeting with Professor Yang.
Okay, I will turn to Chinese to present my speech. So today I will talk about, from the end customer's point of view, the development process of macro and mini LED. Next slide, please. Yeah, so for my speech, I will cover the following 3 aspects. First, about the development of mini LED, and the second, in the process, for the key issues, what are the key technologies we have, and the third, in the mini and the micro LED, what are our products? First of all, I want to cover the first part. From the end customer's point of view, I want to show you in the future how will be the future display like. We define as 6U in terms of the display's point of view. As for the ultimate display, there will be 6 U's. First of all, unlimited size, and then unlimited ratio, and then unlimited form of products. And number 4, unlimited border of products. And number 5, unlimited resolution. And finally, unlimited interaction between people and machines. So we believe that the 6 U's will be the future trend of display in the future. And we will move towards the 6U in the future. Next slide. Yeah. So here you could see that the market opportunities of mini LED. Actually, the mini LED market has 2 parts. One is the backlight, mini LED BLU, and the second, mini LED direct display. For the backlight, we cover TV, monitor, tablets, mobiles. So we could see the BLE cover the whole sizes. Direct display covers 2 important parts. One is PID, the commercial market, and the second, the automotive market. So for the market opportunities, we believe there are a lot of market opportunities for mini LED BLU and mini LED direct display. And now let's turn to the market trend. We have seen 3 market segments. The first is mini LED backlight TV. Second, monitor, and the third, backlight and B market. In these 3 market segments, in terms of the mini LED backlight, it is growing quite rapidly every year. And the growth rate is very high. In 2025, there will be over 30 million units sold, so the market will be huge. And then let's turn to the direct display of small pitch.
2.5以下的整个市场全部都把它列出来。那
Here I have listed the market below 2.5. Different colors represent different segments. We focus on below P1.1. For market of below P1.1, the market rate, the growth rate is the highest, over 50% in China. So this shows that in the future, we will grow towards below P1.1 or even lower.
0.9
And now we cover from 0.6 to 0.9 as the main market. If we go below 0.6, then this market will turn from mini to micro. So for the direct display, we have some existing market in mini, and we will go towards micro. As for the end customers, I believe that there will not be clear separation between mini and micro. Instead, there will be the minimization of micro LED. So the direct display market is huge, but I want to draw your attention that if we don't consider the changes, only look at the existing market, then this is the market of just $2 billion USD. But if we don't move into the consumer electronics, the market is not that big. So we will develop not just in the commercial market, but expand in the commercial market, but we will also go towards the consumer electronics to see whether we could reduce the cost and find opportunities. We hope to make breakthroughs in these two parts. Yeah, and next I will turn to the overall industrial chain. Actually, in 2020, in this whole year, the market of mini and micro LED is active, not just for high-end customers like Apple, which is promoting the monitors and other related products. Also for tablets or upstream chip producers, they all work with each other in different forms. So to accelerate the development of mini and micro markets, that is a very clear trend. Next slide. Yeah, and now let's see that for the development of mini and micro, there will be two big trends. Now the mainstream market is mini LED, and for the future mainstream market, there will be POG, POB, packaging on glass, and packaging on PCD plate. So these two trends will move towards COG and COB. And such a change will change our resolution and precision. If we work it on PCB, then that is PWM driving. For the mini chip, high resolution, we cannot do that. For the large system, small chips, low brightness, PCB will be restricted. So we believe that for the future cost and driving, they will move towards COG. That is the end for us. But during the process, there might be POG and POB solutions because we want to solve the fast commercialization and also solve the issues which couldn't be solved through the mass transfer. We hope through the existing plan, we could commercialize our products. So that is like the mid plan. Next slide. Yeah, based on the overall understanding of the market and the analysis of the market, we could see that if we want to solve the mini and the micro technical commercialization, we need to make breakthrough in the following 4 perspectives. And there are challenges in these 4 areas. One is in the chips. And we need to develop the 03, 05, 06 chips. And also, apart from the market, if we want to go further, we need to consider 2 parts. One is the minimization of chips. We want to make it micro. Also, we need to consider how big the overall volume is. And the second, If the chips are smaller enough, then what about the yield rate? What about the overall efficiency? Could we enhance the overall efficiency to meet demands? These are the two areas we need to solve. If we cannot solve these two, and if we find a middle process, then we could find like 0-in-1 or 2-in-1, which consider both the cost and efficiency. And then the backplane. If we want to achieve AM, then we need to consider for the existing driving unit, LGPO, what are the choices we have? So after our analysis, we think we could consider in following perspectives. One is the brightness, and then the size, and then the overall precision of backplane. We need to consider these three. If it is less than 2000 at peak brightness, over 0.3 pg, then there will be huge possibilities. But if it is less than 0.3 and the peak brightness is over 4000, then we need to use LPDE. So we need to consider the overall size and precision requirement. And now let's see the compensation technology. If we need to use backplane, we need 3GC. So to achieve the internal compensation issue, we may use IC, that is a key technology for us. And the fourth is the transfer technology. That is also a very important part for the commercialization of microchips. We have researched in different perspectives, like the laser transfer or others. We are working on it to try to make breakthrough. So these are the 4 areas that we want to make further breakthrough, so we could achieve the commercialization of mini and micro. Next page. And now let's see, for us, while we try to make breakthrough in these 4 perspectives, what are our overall strategy? We have different stages. The farthest is the mini backplane. We already achieved that in 2018 and launched it in 2018. And then we have the backplane 2.0 version. We might go to high-speed IGB, and then we will do AM on glass. We would do the small pitch direct display, and then we will try to make breakthrough in the with the transparent glass and flexible PI. We will promote the transparent and flexible LED, micro LED. That is the future trend. Next page. Well, for us, we will work in the following 4 areas, and we call that PACE. This also shows we will develop at different stages. In order to commercialize, we need to consider different perspectives of products. So first of all, still the picture quality, and second, the appearance of the product, and third, LED and overall efficiency, and fourth, energy saving of the product. So I will talk in these following 4 perspectives. How do we ensure the products? Next page.
And talking about the quality, the first part is that the university of the picture quality. We're going to consider this part from 3 parts. The first is a M-on glass driver, and also whether or not this is going to give us some kind of a deviation and displacements. So we're going to have this particular kind of a structure to really redevelop the whole process to make sure that this is quite consistent. And second thing, nowadays, in terms of the micro and mini LED products are made, the consistency and conformity should actually be reflected in 2 parts, the LGD's conformity and also the luminance. So we are going to have the formula algorithm to have a combination to really realize the improvement of the picture quality. And third of all, we already started the process that talking about the real effects of the real products, we're going to have a kind of a backward forecast to see that in a wafer fab, what kind of a production should we do? What are the width? What are the luminance? What are the kind of voltage? And how to distribute In the very beginning, we have to use all kinds of different algorithms to have this particular process. So through these three major things, we have to make sure that the picture quality is actually quite consistent. And also, talking about the driver perspective, probably you already know that in this particular industry, talking about the mini and micro LED, we have three drivers. One is PM driver, the other is AM micro IC, and the other is AM TFT driving. And these three driving methods are having their pros and cons respectively. For the TF part, so as I already stated, that among the three major driving methods, the PM driving, as everybody knows, that they use a lot of PW drive, and also on the glass panel, we have all the wirings. And also for this particular driving, the problem is that it is using time to adjust the luminance, while the luminance, we want to make it very high, and I use time to control. And also, as for the current requirement of the chip or IC, this was going to be very high. So normally the current will be very high. So because of that, we have another kind of a method of some active method. And next to it, we have the AM micro IC. It can be one-to-one or one-to-multiple. I can actually reduce the current, and also the drivers inside product could be quite simple, and back panel will be quite simple, because I already realized the moves. And also to make a micro IC driving, stability is good, but cost is high. And also, if we make it on a glass, the TFT has a very high precision. And also this is a high precision kind of a explosion proof. And I don't need to do any wiring, can be very precise. I can use the existing modules to do driving. So the pitch can be very, very small, and also luminance is very high. And also in terms of the driving cost, it can be further reduced. So actually talking about three major ways of driving, we are still focusing on the MTFT. But whether or not it's LTO or LTDS, this is going to be subject to different form factors and also the product features. And also take a look at this particular kind of a compensation, optic compensation algorithm. If we don't do any kind of a processing, the mosaic and also is going to be very severe. So that to say, for this particular algorithm, this becomes very important, and also sealing is very important. On the right-hand side, we have evaluate the final effectiveness from the data-driven all the way to processing and algorithm compensation. You can take a look at the effects, very, very clear, right? And obvious. If we compare the kind of color gamut as well as the quality and also the luminance, very good improved. So you can see that the data volume, on the other hand, is massive. So this is something that we're going to try to resolve in the future. And also take a look at the appearance. It's because I made it on top of glass, so I have to think about two things. The first is appearance of the product, and second, how to mix and match. So if we put it on the glass, the matching kind of capabilities are two. First is the narrow bounding, the other is the back bounding. So for the narrow bounding, actually the problem is that the pro is that we don't need to develop new facility because the cost is cheap, but the pitch cannot be as small as possible. So I think that the pitch can be as low as 0.9, but if we want to lower it further, we have to do a super narrow bonding technology. But if it's back bonding, we can do a very small pitch. But the thing is that we need to have hundreds of millions of investment for the facility. Another is extremely dark. And also you can see that if the IC is big and also the pitch is very small, it is like I have a lot of mosaic on top of my wall and also reflecting lights very seriously. So the contrast will be very poor. But how to make it a very consistent black and dark without changing information, I have to reduce the size of ICs, and also for the sealers and also for the kind of a surface, I need to do a lot of processing. So for this particular part, this is something about the extreme dark. And also I think that, one is the kind of processing of the IC and also some kind of a consistency treatment of the SMT. And another is surfacing processing. So for example, one is for the interface and the other is kind of a restructuring of the formula of the sealant. So we can make the contrast as beautiful as possible by doing that. And then take a look at the capacity. So for capacity, we need to take a look at two things. The first is for the wafer production capacity and efficiency, because we know that there are two problems for the manufacturing of wafer. First is small IC in lack of demand, in lack of capacity. And second, the single kind of a productive capacity, this is not enough as well, because for the rest of the bin, I cannot use it. For current lack of capacity for the single bin is restricting the production yield as a whole. So we are collaborating with our partners to solve this issue. The other is the transfer efficiency. So now for the traditional kind of a dozens of K kind of a technology for the UPH, how can we actually change it into hundreds or even thousands of K per hour if we cannot make a very good improvement of UPH or the yield, and we are having a lot of limitations over the transfer efficiency. And also, if we need to do productization, there's a big problem because of the limited UPH. And also, take a look at this particular improvement of the production capacity of the IC. First is that we're going to make the IC smaller and smaller, and there are a lot of restrictions in the future. And now, in China, for the major manufacturers, with regards to the ICs manufacturers, there are a lot of problems. Yield and capacity are not enough. And second, if we're talking about the whole process, if the ICs and also transfer technologies are not developed, I want to improve the efficiency of transfer. You may be thinking about using 8GB 1-in-1 or 4-in-1 RGB. That seems that the transfer efficiency can be hedged. So we're going to actually choose some kind of a middle ground solution. But the problem is that when I'm illuminating, the quality of the picture is going to be impacted. So you can make the size very small, but the illuminating unit is packaged. So let's just say the picture quality is going to be influenced. So finally, this part is extremely important. And also taking a look at the mass transfer. So here I only put 2 transfer. Why only 2? Because for the electrostatic and also luminant, we have given a research to it, but in a short period of time, I think that in the short period of time, the quickest way should be focus on this. This is only my opinion, right? I believe
Chao,
that the laser transfer should be the most important thing. Okay, I may try to be quick. So these 2 technologies should be breaking through. And I think that this is the most efficient way for us to have a breakthrough. And another part is the energy saving. We're going to consider 3 things. The first is LED, luminance efficiency. Second is the transfer, and also migration efficiency, migration ratio of the back panel technology. Third is the IC energy saving plan, and then reduce energy saving as a whole. Currently speaking, there is about 1,000 kilowatt hour above per square meter. So very, very high energy consumption. So we need to do further adjustment in the future. And also talking about the IC, I may skip the details. So normally speaking, we're talking about the kind of efficiency improvement for the internal and also the external quantum. And also, very quickly, telling you the China Star's product. The first is backlight product, the 75 inches 8K MLED, and also the eSport MNT. So we are already realizing the productization because this is backlight product, so very quick and also very quickly realized. And also taking a look at this TBC 2020, we announced and launched the 142-inch FHD mini LED IGZO on-glass product. And also, we realized the illuminating, and also we have solved a little bit of the problem. And next, we're going to try to make the machine as small as possible. And also 4-inch IGZO micro LED. Normally speaking, the kind of, for this part, we are also trying to illuminate it. And we're using the staff mass transfer technology to make it in-house by ourselves. And also talking about the future, we are trying to pay attention to the kind of flexible and also the transparent direct display and some of the samples. And you can see the details here. And we are doing continuously the testing. And also in the future, we're going to have the positioning of our products in the future. All right. So much for my report. And next, for the whole industry, if we need to make it successful, we need to have a combination of upstream and downstream to realize, reduce the cost, and also improve the efficiency, and finally productize very successfully. Thank you.
Thank you so much, Chia-Hsin, Mr. Chao, it's been really, truly fantastic. I would like to ask all the people who have a question to write so in the chat and raise the hand. But I wanted to start with the keynote presentation from Professor Chao. Before we have your question and answers, I have now the huge honor of introducing the people who made this fantastic meeting happen. And those are the Secretary Generals of the three fantastic associations today. I have the honor and pleasure to introduce the Director General of EPIC, the world's leading photonic association, Mr. Carlos Lee. Thank you so much for joining the meeting today.
谢谢 Jose， 我会说中文，为什么？
Thank you, Jose.
我
I'm speaking
中文
Chinese.
我知道我的中文不太好，但是
I think that my
燕
Chinese is not that
他
good.
说英语，所以我觉得我是
But
欧
Yan
洲
is
人，我
Chinese
要
and
说中
he's
文。
speaking
可能
English,
我的
so
中
I'm
文不太
European, I
好，
should speak
我学
Mandarin.
中文学了
I
5
may not
年
have
了，
a very good
所以
Mandarin
对不起，有的东西
ability.
你
I've
们
been
不
learning
明白。
Mandarin for 5
但
years,
是我真
but
的
I
觉
probably
得
not understanding
帮
everything
助
well,
欧洲公司、中国的
especially
公司合
professional
作是
things. But I'm
最
really
重要。
helping Chinese
所以
companies
我
and
非常高兴
facilitating the
我
Chinese
们今
company
天
to do
可以合
innovation
作，
is
这个
more
是
important.
ISA、
So I'm very
PIDA、
happy that we're
EPIC
going to have
可能
EPIC
安
SID
排这个今天的
for
晚上
arranging this
一个
particular
会议。
webinar and also IC as well. Thank you very much
非
for
常
your
不好，这
organization.
个疫情是我们不可以
So
出
sorry
差，
for not happy
不
for
可以
not
出差的时候
being
我们
able
不可以
to
见面，我们
have
不
the
可以
offline
见。
meeting because of
我觉得
pandemic
电
and
视
we cannot
很
meet
重要，
each
因
other
为
because
重
of
要是我
pandemic.
们认识一
I think
起。
that the
但是
meeting and networking should be
为
very
继续我
important
们可以我们
and
可以
we
网
should
上
make acquaintance of each
有
other.
这个会议，
However,
有一个好处，有这个翻译，
online meeting
所以
has
可能有
advantage
中国人，可能是
of
有欧
time
洲人，
saving and also
我
travel
们可
saving,
以
and we
学
do have
习我们
translators online.
的
And
技
also
术。
we can actually
因
learn technologies
为
from
最
different
重要
countries.
是公司
And the most important
公司
thing
他们生产产品，
is
他们
that
发
the
展
company
他们发
is
展技术。
developing their products and
我觉
developing
得
their
有很多
technologies.
的机会我们
And
可
I
以
do
合
think that
作。
there are more opportunities for us to
所以
collaborate in the
我
future.
想要给你们我的微
So
信， 等一下我给你
I
看，
would like
这
to
是
give
我的
you
微信。
my WeChat
我 希
account.
望我们可
This is my
以
QR for the
联
WeChat.
系。
And hopefully that we can all keep in contact.
我要告诉你们，真的，我要
I have to
欧
say
洲
that
中国合作。
I really would
我
like to
非常
collaborate
高兴
with
你们在
Europe
这儿。
and China. I'm
今
very
天我们
happy to see you all
有
here
很多很
online.
好的人，我
And
们可
today
以
we do
学
have a
习，
lot of
我
good
们可以
speakers
见
and
面。
experts, and we
我
can
希
learn from
望
each other
你
and
们
can see each
明
other
白
online.
一点
I
我的
really
意
hope
思。
that
谢
you
谢。
truly understand what I mean when I'm speaking Mandarin.
Carlos, it is great to have you with us this morning. What an honor. I also would like to introduce a person that means a lot to the micro LED industry. I had the honor to co-chair this event with him, Secretary General of SID, Professor Frank Yang. It is a special honor for me to have you with us today.
Okay, thanks, the host, and also it's my great honor to be here today also, and also welcome everyone, and good morning or good afternoon, wherever. And it's my pleasure to be here, and also we'd like to thank all the speakers from either from ISA or from our EPAC and from PIDA. And again, we really like this opportunity to bring the China and Europe and also other region of in the world together. I think this is a great opportunity for the company in China and also the company in Europe, so they can, from this event, they probably can set up some collaboration in the future. So again, it's welcome everyone, and also it is our a little bit of effort. We put things together, and I hope that we can get some feedback from audience, which is very important, so we can make the event in the future maybe much more efficient and maybe more fruitful event in the future. Again, thanks everyone.
Thank you so much, Professor Yang.
Our host,
I also have in the room the CEO of PIDA, Mr. Lin. Mr. Lin will be giving a keynote presentation about mini and micro LED in Taiwan later. But it is so great to have the support of the top people who are leading the associations of micro LEDs worldwide. What a fantastic day. And with this part already done, let's go back to Mr. Chao. Mr. Chao, you gave a fantastic presentation. There are a few questions in the room. The first one is from my side. You had a fantastic slide showing the different pitch reduction that you are targeting in the coming years. You said that going below 0.9 could require a large investment. My question is there a market to go to such a small pitch reduction? And if it is there some room for cooperation with other companies to help you get there?
Hope our translation goes through.
Yes, it's okay. People can wait for this silence. The question is being translated. I will simplify the question, Mr. Chao. How small in the pitch reduction would you like to go in the coming years, and who can help you?
Hey, 肖博士在线吗？
Seems lost the connection.
Okay, we lost the connection to Mr. Chao, but we will come back to him afterwards for answering some of the few questions we have, like the one from Ruby about silicon backplanes needs. We will come to you afterwards to ask these questions. Why don't we move to the next speaker today? And the next speaker is representing one of the big success stories of automation in Europe. We're going to talk about micro transfer printing and a company who made it real for the micro LED world. Alexandre Chikhaoui is the business development director of X-Celeprint and also a friend of mine. Alexander, thank you very much for being with us today. X-Celeprint is a jewel of EPIC. The floor and the attention of everyone in the entire world goes to X-Celeprint.
Hi, Jose. Thank you very much for the introduction. I hope everybody can hear me now. Thank you
Loud
also,
and clear.
for inviting us also for this call. So we don't have many time, so I will go directly to the point. Today, I'm gonna present you about how do we form micro LED using micro transfer printing technology. But also I wanted to divert more into the 3D heterogeneous integration and how we can penetrate other markets than displays as well. So, and now I need to go to the next slide. I will make a very short introduction. X-Celeprint is pretty famous in the display industry already for micro LEDs. We are, developing micro transfer printing technologies. We're adapting the technology with our customers, and we are a licensing company, right? We have key markets that we address, like photonics, power management, automotive, medical, automation. And you may notice display is not written here. And this is what I wanted to explain, is that in end of 2019, X-Celeprint has spun out another company called X-Display. And that company is actually developing MTP for displays and also licensing and selling products. So this is just a little parenthesis to understand about it. So regarding the technology of MTP, this really enables true 3D heterogeneous integration. This technology can extract components from any source, gallium arsenide, indium phosphide, gallium nitride, and I will not go through the whole list. This technology can manipulate extremely small components down to 1 by 1 micron type of components. This technology can manipulate extremely thin components down to 500 nanometer. And this technology has also a very high throughput because you can transfer 100,000 or 500,000 of components in one go. So those characteristics makes this technology very ideal to build 3D heterogeneous integrated systems. And also, this technology is in mass production. So this is important to notice that. For a long time, we are producing for solar. Very recently, we are producing for LiDAR systems. And there are going to be soon some announcement of some high volume production in the photonics industry. And what you can see on the right here is a production printer, the MTP200, which is available from XDC company. So what the subject today is about mini LED and micro LED. And the next slide is, I really like that picture, showing you a comparison between a mini and a micro LED. So this picture talks by itself. There's an SEM on the left, you have the mini, and on the right, the micro. And what is interesting to notice is this huge difference in thickness, right? You can see the XY direction, which, here we can have like 80 by 125 micron on the left, or maybe 80 by 90 micron on the right. But ultimately, the main difference is thickness. And that drives actually the application for micro LEDs, where you need the component to be extremely thin. Micro LED can be used. That also drives the way you interconnect things. You cannot do thin film metal interconnect with a mini LED. You have to use a flip chip bonding. With micro LED, you can use both. So I really like that picture. This is a courtesy picture from Lextar. You may know it's public that Lextar is an MTP licensee for micro LED for display. So let's go now to the next point about how do we form the micro LEDs. Here is an example of a process flow where we are creating micro LEDs out of GaN on silicon micro LEDs. So it all starts with the epitaxial wafer, right, where the substrate is silicon. We have a release layer, then we have a GaN material grown on top of the release layer, doped with the P and the N. The next step that we do is that we are actually forming the micro LED by etching down the GaN down to the release layer. The next step is to add ohmic contacts, and then we're adding dielectric to form the anchor and the tether that will hold later on the LED. The next step is to reinforce the contacts because you want to reduce, of course, resistivity, and you want to have thicker metal lines. And the final step, you're releasing the release layer. And this cartoon here doesn't show it very well, but this picture shows it better, right? At the end of the day, your device, the micro LED here, is kind of floating off top of your wafer. The release layer here has been chemically removed. It's held by its tether and its anchor. So this is a picture of the top view of the wafer where you have multiple micro LEDs aligned here. And that's what we call our print ready wafer. So the micro LEDs are ready to be transferred to the display backplane. Another picture here is talking about GaN on sapphire micro LEDs. I'm not going to go through the process flow of how we can get GaN on sapphire micro LEDs, but this slide is really to emphasize the different method of interconnection. On the left side, you have a flip chip GaN on sapphire micro LED. It has bottom P and N pads, and this is a method that we call interconnect at print. So as we transfer the LED, the galvanic connection between the P and N junction and the metal lines that we can see here, right, are interconnected as we print them. This is a very useful method of interconnect, especially when you want to move to a display repair, which is necessary to achieve high yield on displays. On the right side, you have another method of interconnect. And as you know, the micro LEDs are very thin. And now thin film interconnect is another possibility of interconnecting the LEDs. It might not be the ideal method to interconnect for displays, but it could be a very useful method to interconnect for other type of application. An example of a PSS GaN on sapphire micro LED, and those I think are from Lextar. And the bottom picture is just to show that the LEDs are interconnected. And as soon as you interconnect them, you can light up your display and make a visual inspection if the pixel has been well printed or not. So as I said, we worked and we have processes for GaN on silicon, green and blue micro LEDs. We have processes for GaN on sapphire. We have processes available for gallium arsenide red LEDs. We can handle lateral and vertical structures. We can handle top pad and flip chip and various sizes. And here is a real-time video of a micro LED transfer. So you will see here those 4 LEDs now just have been picked up and are going to be transferred to the display backplane here, thanks to our PDMS stamp. Once they have been transferred, the PDMS stamp is moving now to the clean pad, which basically is a Scotch tape to remove all the dust and to increase the number of pick capabilities per wave per stamp. And then the stamp is coming back to the source and is picking up the next 4 LEDs here. And the takt time here for the whole process, I mean, you've seen it, it's live, it's about 20 to 25 seconds. And you don't only transfer 4 micro LEDs like you can see here because of the field of view of the camera, you're actually transferring 10,000 posts on that video. We can transfer 10,000, 100,000 or even more devices in one go. So the next thing is I really wanted to emphasize what we're doing for the 3D heterogeneous integration. You've seen on the previous slide that we're transferring single LEDs, right? But our next step was actually to build micro packages where we could interconnect together 1 red, 1 green, and 1 blue micro LED into one package. Here the size is 70 by 35 micron. And that small package can then be transferred to the display backplane, for instance. Then we went further and we succeeded to integrate LEDs. Here you can see 6 micro LEDs, but they're on top of an IC. And that IC and the LEDs are fully packaged, and that's what we call the pixel engine. So you have here an active pixels with 6 LEDs and an IC, and that can also be transferred to the backplane. So this is really the base of the 3D HI integration. And this is how X-Display also is operating. And that's why also X-Display has been spun out and is developing further the technology for displays using this pixel engine technology. They're doing a fantastic job since a year, and they have developed the technology further. And this is really, really impressive what they have been able to achieve. So 3D HI enabled us to move from active pixel into the display field. But what if for each of those active pixels, you were adding a sensor? This is feasible with 3D HI integration, right? And so when you're adding a sensor, then suddenly your pixel starts to be intelligent. There's many, many medical applications which using very thin medical patches would need that intelligence, right? You can see here a picture and cartoon showing a flexible micro LED array on top of a patch. But what if each of those LEDs were actually a full system with micro LEDs, with a sensor, with a driver? The possibilities are infinite. Here it's showing about photostimulation application into the medical, but you can guess easily that you can go to many more applications. And we have a very high interest into those applications, and even have recently some licenses in the medical field. Another type of application is automotive. I know we're going to talk later about automotive, but here it's not about micro LED into the automotive display, micro LED display into the automotive world that I'm talking about. I'm talking about the interior lighting. So the number of LEDs into the car are increasing a lot. And all the integration method of light guides, all the control method will have to change because the number of LEDs is growing. And here comes the need of potentially intelligent pixels, which do not only contain the light generation of micro LEDs, but who have also the LED driver like the active pixel, but we can have also a microcontroller and bus interfaces. So this is also another application of 3D HI micro systems that could go into automotive. Another application could be authentication. Again, there is no limitation in 3D HI integration. You can have LEDs, you can have a controller, memory, and you can have also power harvesting devices that generate its own energy. So really what I wanted to say through that is that, you know, this is the great value that X-Celeprint bring in 3D HI integration beyond displays, and the applications are really, you know, infinite. And I will finish here with my last slide, mentioning that the MTP adoption and the ecosystem is growing. You can see here that we have multiple R&D prototyping lines at X-FAB, at Micros, at Tyndall Institute, mainly based in Europe, at IMEC, but we also have in US some R&D lines. Something which is completely new, it could be a scoop maybe today, we have our first MTP ready foundry service by X-FAB. So today, if you would like to have an MTP-able, transferable, and micro ICs made in CMOS technology, this foundry service at X-FAB is available. It's online on the website of X-FAB, you can have a look. So this is very new as well. The manufacturing systems you need for the manufacturing and for the MTP mass transfer, you need a tool, right? So XDisplay is one of the tool manufacturer. And also here, this is new information for everybody. ASM and Micra is doing mass transfer tools that are available for sale for MTP licenses. And the most important one, of course, we need in this ecosystem customers, and we need LED companies moving into that. So OSRAM is one licensee of X-Celeprint, and Lexstar in Taiwan is another licensee of XDisplay in the field of displays. We have many more licenses. I mean, we're talking about publicly disclosed ones. And this is what we're really trying to achieve now, is to make this ecosystem grow. And I hope that I haven't exceeded the time too much, but I would like to thank you, everybody, and I'm open to any questions.
Thank you very much, Alexander, CSE, for a great presentation. It is great to have you with us. We have a lot of questions for you in the room. So I would like the questions to be asked by the question makers. And we are gonna go first to Comptek Solution, one of the key companies in EPIC making equipment for passivation technologies. Jouko, what's on your mind?
Hello, yeah. Thanks a lot, Alexander, for the very nice
Jouko,
presentation.
don't be shy. We are not shy today. Switch on your camera.
Oh, sorry, that was.
Thank you so much.
Can you hear me?
We can hear you. We can see you all the way from Finland. Jouko, what's on your mind?
Yes. So I was going to ask that is there any performance penalty after the transfer? So if you compare the micro LED on a wafer compared to the transferred micro LED, so is the performance still the same, or is there any penalty after your process?
Yeah, I mean, we have made enough experiments to confirm that there is absolutely no penalty after transfer, okay, whether it is about transferring ICs, complex ICs, or even LEDs. So the performance are same, or actually could even be better, because the bulk silicon or other substrate are not, I mean, are actually improving the performance. So yeah, there is no performance change.
Okay, good, thanks.
The second question is coming from one of the success stories of semiconductor equipment manufacturing in Europe, EVG, all the way from Austria. Mokapati, what's on your mind?
Thanks a lot, Jesse, and thank you, Alexander, for really a very nice presentation. Actually, I have two different questions. So one thing is, like, the first one would be, what is the size limitation when you do this transfer? And the second one is, when we have this PDMS stamp, you know, once we start placing it, once you press it, there might be a lateral expansion. So I'm just wondering, how do you cope up with this?
Sorry, can you repeat the first one? I mean, I understood the second question.
The first one is, what is the size limitation of the micro LEDs you're transferring in this case?
Oh, I see. Yes. So, I mean, there is no real limitation. I mean, I would say 1 by 1 micron is what we think is a good, minimum size. We haven't tried below, right? But it doesn't mean it's not possible. So, and our first micro LEDs were 3x10. So, but then it's really about your application. Maybe you need larger LEDs to generate more lights. But so that's why we think it's not a limitation, really. The second question is, when we transfer the LEDs, no, there is no expansion. I mean, we're transferring the components. The PDN is actually soft, so there's not much pressure applied to the component. So the component itself is not damaged. What could happen is that the component may shift because of the adhesive that is on the target substrate, but those are controlled processes, and we can avoid that now easily.
The next question in the room, Alexander, you are going to like it. You're going to like it very much. Rashid, what's on your mind? I will read it for him. What is the current yield and accuracy that X-Celeprint can reach?
Yes, I mean, our current yield, I mean, it's a very large question, right? I mean, it really depends on many things, but we can comfortably reach 4 nines, 99.99% in transfer yield, right? When you're talking about accuracy, we started with 1.5 micron accuracy, plus minus. We can also reach 1 micron or less, right? It's really a function of how many components you transfer versus the accuracy, right? So yes, I mean, this is definitely enough in terms of accuracy for the size of the components we're using, yes.
I am extremely excited for microtransfer printing when it comes to yield and when it comes to throughput. So that's why I also love that question. And the final question is coming from one of the success stories worldwide on maskless lithography, grayscale lithography, Heidelberg Instruments. Dominic, I believe you have a broader question for the whole event, but let's ask now and let's get first Alexander's impression.
Yes, good morning to everyone, and thank you, Alexandre, for the presentation. I'm pretty ignorant in the process of fabrication of micro LED, but my question is quite general. So how maskless lithography or grayscale lithography could be helpful in the process of micro LED fabrication?
Well, we're not using maskless lithography at this stage because it's not necessary, right? However, if you want to move to even smaller components, right, that could be necessary, but this is not necessary at this stage. So I cannot really comment more than that. We're not using it for the moment.
But Dominique, later in the meeting, we are going to have presentations from BOE, Mr. Wang. We are talking here about one of the leading companies in bringing new technology to display manufacturing. You should ask the question then. I would be very excited to know the answer. But first, I would like to now say to Alexander, congratulations on what you are achieving. It is a success story of the European industry, and having seen you collaborating with companies like Amicra, already making ASM Amicra, already making the equipment for the production, gives me goosebumps. Keep up the fantastic job.
Yeah, thank you very much. Thank you, Jose.
We moved with the program, and now I had the honor to introduce the other worldwide renowned association that is with us today. We have PIDA in the room, and we have it represented by the chairman, Kenneth Tai, by the CEO, Mr. Lin. But I want to go to Kenneth Tai first because he's also a personal friend of mine. Kenneth, thank you so much for being with us today. It is 9:59 in the Netherlands. What time is it for you? Kenneth, we can see you and I think we can hear you.
Yes. Okay, yeah, okay. Hello, everyone. Good morning in Europe. Good afternoon in China.
Good morning.
Yeah. Today, I'm honored to have, on behalf of the Taiwan photonics industry, to introduce some of the good companies are successful in micro LED area. The first one is a government-owned ITRI, Industry Technology Research Institution. It's a very good partners for research and the development. Nitride is a very successful company in the mini LED, one of the leaders in the world. And the Southport, there's automation, testing, and the metrology inspection. They will be the leaders. PIDA is Photonics Industry Development Association. Yeah. Its mission is education to provide the talent. It's a research and the development, and also international corporations. I think one of the important things is China and the US are very big. Okay, and the Europe, and the best partner for Europe possible is Taiwan. Because Taiwan needs Europe. And I believe Europe also needs Taiwan. We are the gateway to China to help the Europe partners. Just give you a number for reference. Our export to 150 billion US dollars. That's a huge numbers. And continues to grow. The growth rate is 15%. And the IT related, the broad IT related percentage about 65% is in our category. So in the technology area, I think Taiwan will be a very good gateway to help Europe partner to enter the China market. Let's talk about the IT industry as a summary. Just give you a briefing. For the I think percentage. We have on about, I think at least 80% or above. Notebook is the same thing. Server, it's also same. Because these three applications are all office related. So no matter you are in Africa, China, Europe, US or Taiwan, it's all similar, yeah. And I believe because of this still technology is a core. Taiwan continues will win this market for next 10, 20 years, I believe. But unfortunately, Taiwan lost the cell phone market. The smartphone products is not due by Apple. It's really the first two generation is from Taiwan. But because of it's related with the daily life, so Taiwan lost the market.
Kenneth, we are running out of time
in this industry.
Mr. Kenneth Tai, chairman of PIDI and personal friend of mine, we are running a bit out of time, so if you could maybe speed up a little bit now,
Okay,
so we can.
The second page is the next page is talking about a silicon foundry, not only silicon foundry but also 3-5 foundry, and also packaging, testing, and the whole supply chain. That is a very important message to our Europe partners. We can claim Taiwan's technology density, Taiwan is the best in the world. Okay, then I talk about another product important. It's IC design, including silicon, potentially come to silicon photonics, and also X on CMOS. That is a material, it's a so-called heterogeneous integration between material and the circuits. And the PIDA's scope of photonics industry, we claim there's optics, optoelectronics, and because we are very strong in silicon, so we separate electro-optics. And then we add on another very important category, is the material science and equipment. Taiwan is the biggest buyer in both equipment and the materials. The next, we talk about the micro LED ecosystems, including the device and the display. So in every category, we all have important players. I'm also the JDC's CEO. My device is active matrix digital modulation. That technology, we are the leaders. And the backplane is 40 micrometer below. Yeah, down to 2 micron or like that, okay? Then I think what I like to promote the Opto Taiwan. Opto Taiwan, we were promoting the technology. So the category, I will not go to the detail. Yeah.
Kenneth Tai, thank you so much for this great presentation,
And
and
then,
thank you.
Next page is all the communication. So we go through the line, Facebook, in the link, and the YouTube.
All the different
So please
communication
follow us.
channels to
Thank you.
connect and interact with PIDA, all the way from Taiwan, bringing the industry together. Kenneth, you are an example from this industry. With your vision of digitization of the photonics industry, you have been a big driver of photonics. Kenneth, thank you so much for being with us. I would like to now continue with the program. We have, I had the honor of introducing our next speaker today. Our next speaker is Chia-Hsin Chao, Manager of Electronic at ITRI, or ITRI, as some of us know it. Mr. Chao, thank you so much for being with us this beautiful morning in the Netherlands. What time is it for you? Mr. Chao?
Yes, here.
Yes, it is 10:12 in the Netherlands. What time is it for you?
Okay, here is 5:12.
All right, so let's start. The floor and the attention of everyone goes to you.
Okay, thank you very much. Good afternoon and good morning, everyone. It's an honor to be here. I'm Chia-Hsin Chao, belonging to ITRI. The topic I'm going to talk about is micro-LED 2.0. From display to heterogeneous microassembly system. It's more about the next step of our micro-LED research in ITRI. The outline of today's report, I will go through the introduction, ITRI's total solution for micro-LED, and what we are working on for the next generation micro-LED technologies. Active Smart pixel package is a kind of a pixel package including RGB micro-LEDs, micro-driving ICs, and the sensor on it as well. Micro-LED for AR display has very high PPI micro-LED pixels on the most backplane IC, featuring very high brightness for over 20,000 nits. And the last one is eye tracking application using micro-LED as sensor, which is integrated with AR glasses, providing the eye-machine interaction interface. Micro-LED in recent years have seen rising attention due to their supreme quality of the displays. Among the current display technologies, micro-LED is in several categories like brightness, power consumption, contrast, and lifetime. All these advantages from this device are very important for a future display device. However, the cost structure is still in development, and the last micro-LED based display is very expensive. For the certain applications such as esports and augmented reality, they do have different requirements for the display device, and we believe micro-LED can fulfill them all. In ITRI, we started our micro-LED research back in 2009. From a very simple passive driving matrix and a single color micro display using Jasper display backplane IC. We gradually move on to the full color technology with mass transfer method. In 2020 CES, we demonstrated the first large area micro LED based display on a sprint circuit board, which is much difficult to work with. And now we are working on very high resolution, close to 2000 ppi for AR, MR, and automatic displays with micro IC driving for high brightness. In ITRI, we have set up two important platforms to serve industrials. One is the chip fabrication platform, and the other is the mass transfer platform. For chip application, we have a class 10 clean room in our lab, and the full capability to do etching, thin film deposition, and metal coating at Central. For mass transfer, the fully functional line was set up to accomplish our recent demos, and several important functions like initial LIV test, morphology inspection, chip transfer, optical inspection can all be done in ITRI. All these are ready and expecting to work with industrial from the world. So far, using the chip and the mass transfer platforms, we have demonstrated a transparent display with over 65% transmittance by mass transferring RGB micro LEDs onto glass substrate, micro LED on PCB for PID, digital signage, or indoor applications. Flexible waveform display and the AR micro LED display with very high PPI are what we are doing. For AR high PPI micro display, the integrated single color micro LED array with the current dark color conversion layer has been treated as one of the solutions for high resolution full color displays. It's of integrated with simple spectrums are the multiple functions that the circuit can bring in and the compactness of the overall volume. ITRI can play a role to coordinate whole supply chain to make application commercialization in Taiwan. Kenneth component manufacturer can system and also make the system manufacturer can make sure their product can be mass transfer, mass production. Also, we'd like to mention more a little bit is module timing, which is the key processing step for larger size micro LED display. Timing in general is a technique to piece everything together to get a larger display. It is beneficial because a smaller panel usually can be manufactured with a higher yield. But several aspects need to be addressed. First is the precision in assembly. Second is the repeatable process.
And the third is that we need to achieve a seamless split between a neighborhood piece. There are several things we need to pay attention to when we work on timing. The best case is like in product A, where everything fits perfectly. However, in reality, we are going to see cases in product B, where the glass is tired and tightened in a non-straight way. This can rise from the imperfect location of the set screw in the backplane that did the tightening. In price C, the situation could be the glass edge already got some damage before, either chipped or cracks due to cutting. The stress during the splicing could make the condition worse and shorten the lifetime of the module. In product D, another possibility is due to imperfect cutting of the glass piece. Any slanted edges, non-vertical edges, can lead to extra stress during the process and lead to eventual cracks. So precision in glass cutting and the accurate placement of each glass module are quite important to achieve perfect need. One of the critical techniques we develop in ITRI is the laser cutting and the trimming of the glass. We use the pulsed solid state laser, and the laser optics is optimized to narrow the thermal damage. We can reduce the Lång width from 100 to 15 micron. Another thing that we achieved here is to have edge chipping smaller than 5 micrometers. And the glass is cut at almost 90-degree angle corners. On the left-hand side is the finished module with 2x2 piece of a glass piece together. And the total area is 6.4 centimeters by 3.2 centimeters. On the glass, they are micro LED with passive metal connector. So after we light up the micro LED arrays, we can have a photo like a bottom right plot. The red dashed line shows the actual boundary of the two glass, and we see very tall trace from the tiny, meaning that our preliminary work is successful. Currently, we are planning in a more complicated 3x3 modules with possible more functions on the tiled flexible display. Now let's move on to the second part of the report, micro LED 2.0. In ITRI, we are planning in next generation micro LED display technologies. Referring to You's report on human-machine interface in displays, the end goal for HMI features in display is not integrating everything in the display to maximize the user experience. Make a display smaller than display. Micro LED has small size compared to the whole pixel area size. There is a large area in the pixel to put another else components like micro sensors and the micro driving ICs on it. Lots of functions can bring in to the display. For micro LED 2.0, we are upgrading the mass transfer method to heterogeneous microassembly technology by integrating RGB micro LEDs onto micro drivers with sensing function. This kind of active smart piezo package unit is developing for achieving hybrid sensor interactions with display and AR/MR use. In active smart piezo's, Leti proposed a very smart piezo package concept in which RGB micro LED are integrated onto micro ICs using wafer scale assembly technologies. It addresses the issue of yield, throughput, and the cost by notebook dies, reducing number of mass transfer as well. Based on this concept, we have preliminarily studied the possibility of the novel integrating approach designed in on-wafer no-good die inspection and the safe repair function after mass transferring. It will enable and open up the many aspects of the display applications. One of the display applications is augmented reality glasses. Many giant companies like Apple, Google, Facebook, and Central think MR glasses are very potential to be the next big things after smartphones. The future AR glasses on the right side will be slim and lightweight like normal glasses. And it has all functions that smartphones can do. It provides a display, computing, connecting, internet, and the most important things of the friendly I/O ways, like a mouse and a keyboard for PC and a touch screen for smartphone. We believe this HMI will be eye tracking, which can be achieved by smart piezo architectures of micro LEDs. Generation 1 of AR glasses that we are developing is based on regular waveguide combiner optics to integrate the single color LED array with the color conversion layer, realize the high resolution full color display. Here is the cross-sectional view of our design. This is our timeline for developing generation 1 micro LED micro display for MR. Around 2022, we will integrate it into smart MR glasses with full HD resolution and 20,000 nits of white brightness. Augmented reality is an interactive method to enhance your experience with your surrounding environment. AR/MR glasses could potentially replace a smartphone in the future. To achieve this unmet requirement, large FOV, compactness, lightweight, and the friendly HMI need to be addressed. A great
Mr.
micro
Chao, we are
display
running
with the
out of
high
time.
resolution and the brightness, and with very okay. Very low power is necessary. Meta lens optics plays an important role to strengthen optical engine size and improve the display quality. Also, in addition to voice and gesture HMI, eye tracking will be a promising HMI for MR glasses, providing more friendly interactive way. Eye tracking for wearable MR glasses is potential application of micro LED as sensors. The left side is up-to-date traditional eye tracking glasses, which use 4 tiny cameras and several LEDs to track eyeballs. The most concerned issue by system vendors is unfriendly ID design. Due to the large cameras and the LED components, it's unable to integrate onto the future lightweight MR glasses. On the right side, another eye tracking technology can achieve very high frame rate and ultra-low power consumption, overall at least 5 times enhancement compared to traditional eye tracker. The IR micro-LEDs works both as illumination and sensing functions and are must transfer onto the surface of the glasses. Their size is smaller than 5 micron keeps the glass transparent and clear. It will not block line of sight. The point is no ID design issue needs to be addressed anymore. And NVIDIA also demonstrated this type of sensor-based eye tracking. In this initial prototyping, which used several regular IR LEDs on glasses frame, the tracking accuracy is around 1 degree, and also show very fast sampling rate up to 250 Hertz. For our sensor array base, we use the larger array of micro sensors to improve the eye tracking accuracy to smaller than 1 degree. Micro-LED as sensor array is now category of sensing technologies. In addition to on-glass-based micro-sensor array can be put onto the backside of a smartwatch. For example, it could work for LED sensing and the bio-signal monitoring for precision healthcare application as well. Okay, this slide summarizes the presentation. Thank you very much. Thank you.
Thank you so much, Mr. Chao, for this fantastic presentation, which is full of collaboration opportunities, which is what I like the most. There are some questions in the room of people that want to help you, and I want this to happen after this meeting. So the first question is coming from NKT Photonics, all the way from Denmark, one of the key companies in supercontinuum lasers and specialty fiber. Hussein Iman, thank you very much for being with us. What's on your mind?
We have done some thin glass processing with ultrafast lasers before, so we were just interested to hear a little bit more of the requirements that ITRI have for the glass cutting and to see whether we can help.
Mr. Chao, the question is about glass cutting. What are your challenges?
Well,
the cutting accuracy and the cutting angle area, we hope we could be less than 5 micron.
Okay, less than 5 micrometers.
Yes.
If you want to go less than 5 micrometers, even a lot less than 5 micrometers, even less than 1 micrometer, we have companies in EPIC that can help you. And I would like to recall companies like Workshop of Photonics in Lithuania or Inolas in Munich. They are doing fantastic job on that. The next question is coming from the company AU Optronics. Andrew Liang, my friend Andrew, what's on your mind? Andrew is wondering about the test that you follow for the testing of micro LEDs. What is the process for testing micro LEDs? Do you just do LIV, light current voltage test?
We have inspection including LIV testing and the morphology testing and the optical inspection.
Okay. I would like to go to the next question. It's coming from Hopto. Hopto, you are wondering about the state of the art. Could you like to ask the question yourself? They are wondering about if you are aware of the state of the art for USP laser filament spots for cooperation. I will let this to be done after the meeting. I will make sure that the two of you are introduced. I would like to go to the next question.
Okay.
It's from Southport. From Southport, Juncheng from Southport. What's on your mind?
Hello.
Hello.
Actually,
please ask your question.
Actually, I just want to say the Southport system with JD6 backplane can do the LIV curve measurement with under maybe 10, smaller than 10 micrometer micro LED.
Okay, so he's commenting about the size of the micro LEDs, especially the size of the pitch. Chia-Hsin Chao, Mr. Chao, you commented about 6.4 micrometers. Is there an interest to go lower?
Yeah, actually, our goal is to be less than 5 micron.
Fantastic. Chao, Mr. Chao, I want to help you. I have a lot of companies in EPIC that can help you. The next one can help you. We're going to go to Dresden because I have a question from Uwe Vogel from Fraunhofer FEP in Germany, a research center that made mastering a knowledge on micro LEDs for manufacturing in roll-to-roll. Uwe, thank you very much for being with us ahead of displays and sensors of Fraunhofer FEP. What's on your mind?
Hello, nice to see you as well. I have a question related to some of the last slides of the previous presentation. That was actually mentioning integrating sensor pixels for eye tracking in AR glasses. And I was wondering if those sensing pixels are actually on the same die as the micro LED pixels, which would be on a micro display, or are they separate dies, or how does it work? Is it the same chip? Are they somehow distributed, or how is it? Thank you.
Well, for the eye tracking applications, the pixel we use are very less, actually, just dozens of pixel array, unlike the display pixel.
Okay, and I would like to also get one more question in the room. This one is coming from the CEO of Comptek Solutions, all the way from Finland, equipment supplier for passivation technology. Vicente Calvo, what's on your mind?
Yes, hello everyone. Yeah, I just wanted to ask Mr. Chao. He mentioned that they want to go below 5 microns, and I would like to know what are the challenges to get there? What are the challenges they have? And also when they go to so small size and pitch, how they do to fit in all those sensors in between the display pixels, etc. Thank you.
Well, understanding is that to reduce micron, actually we could be very small, even 1 to 2 micron. But the thing is, if the size is smaller, then the efficiency will be reduced sharply. So because we consider the efficiency, so it's not just the size. We consider also the efficiency. Also, when it turns to colorful, we use the big power solution. But if the size is small, then the overall will be more difficult.
Let me remind everyone that when this meeting finishes, we are going to get a link in the chat for all of us to go to the wonder.me website when we are going to get to know each other. So when the meeting finishes, please remember to click on that link that you will receive in the chat. The purpose of this meeting is not only to hear great presentations, but to make new friends. I love doing that. And I also would like to say that I wanted to chair the first part of this event. The next chair is going to be Professor Yang. I had the huge honor to speak before Professor Yang. I will cherish this moment for my whole life. This is my WeChat QR code. So if you want to be my friend, scan my QR code. I will be more than happy to talk to you afterwards. Thank you very much. Xie. Professor Yang, the floor, the meeting goes to you.
Okay, Jose, thank you very much for a nice, host this conference so far. It's a great big honor to work with you for this event. Okay, so I'm going to take in charge of the rest of the event. And again, thanks to speakers and for the previous talks. And I will give the applaud for those excellent speakers and the presentation. For the remaining 5 speakers, and I just want to remind everyone, and we have 15 minutes presentation, so please keep in time. And I hope we can actually have more time for discussion. So, okay, let's move on to the next speaker. It's from BOE. Let's see, it's from Mr. Yuan, Mr. Yuan. So, Mr. Yuan, are you ready? Okay.
OK， 可以看到屏幕吗
Yeah， 可以看到，你能开始了。OK。
Right. So, Mr. Wang, you can start. Ready when you are. Please wait. Let me put it in full screen mode. All right. Hello. Good morning, everyone. And good afternoon. I am Wang Ke from BOE. First of all, very honored to be invited to attend today's webinar and also deliver my presentation. And today, my topic is the challenges faced by the development of micro-LED and mini-LED display. So I have 4 parts in my presentation. The first part is the background of the mini-LED display and also micro-LED. And second is application of mini and micro-LED. And third, the challenges of the development of the display. And fourthly, I'm going to introduce to you the R&D of the micro and mini LED BOE. First of all, the background of mini LED and micro LED. You should be very familiar with this chart. So while we are reducing the size of LED, the packaging way is changing from SMT to COP. And also, the applications are going to found in the lighting LCD backlight units all the way to LED video walls, and also finally to the micro LED video walls. Comparing with the traditional LED or OLED, micro LED has a lot of natural advantages. For example, high EQE, high luminance, and also high contrast, high color gamut, as well as the long life cycle. And also very short response time and also low power. Very extreme advantages here. And also talking about the application of mini and micro LED, there are 3 parts. The first one is the mini LED backlight. Combining together with the traditional LCD, we can realize a super high contrast and also super high luminance. And second part is the video wall of mini LED, so we can have a seamless splitting and to realize an oversized display. And also the third one is the micro LED display. And you can see that in terms of the flexible display and in terms of the transmittance display, they are going to have a lot of natural pros. And also the third part is while we are developing the micro LED and mini LED display, the challenges we are having. So first, in terms of the chip process, because of the unevenness of the etching, there was a sound ground issue. And this particular kind of issue is going to really impact the efficiency of the uses. And while we are reducing the size of micro LED, the kind of application efficiency will be significantly reduced. And second of all, the EQE peak shifted to a high current density area. So that is to say, this is not good for the low current driving as a design. And also, second part is that in terms of the AM driving circuit, we have a challenge. First of all, comparing with the OLED EQE, the kind of difficulties are high. than micro LED, and it's a high luminance. It's not easier and convenient for us to use it as a direct display. And also because of the high EQE area with a very high luminance, so we need to actually introduce a PWM kind of a driver. And also in a EQE area, this is a very big area with a large current. So that is the reason why we need to have a larger area for the driver circuit so that we can actually drive the display. So this is also something disadvantageous to the application of high PPI. And third is that at the low grade scale, EQE is too low and power consumption is too high. And also the PWM design has also a problem of flicker. And the fourth point is for the airdrop and also the topic of lower down the power consumption. And third challenge here is the color purity and also the gamut. And also because of this issue, they're going to actually impact the whole performance of the LED display. And because of different current, the wavelength of LED illuminating is different, and there might be some kind of a shifting. So there is a kind of the color gamut shifting as an issue, and also the chromatic aberration. And also another part is for the mass transfer technology. The mass transfer technology, we need to have a very high precision and also high efficiency and also high yield and also low cost at the same time. And now all the different partners are producing their own mass transfer technology, electronic absorption, and also electrostatic absorption, roll-to-roll transfer, laser transfer, or stamp transfer, or fluid transfer. Amongst so many technologies, I am more in favor of laser transfer. And I think that for the laser transfer, together with our TMT, large size Gen 10 fab, we're going to realize a higher yield with lower cost. And fifth challenge here is in terms of the testing and repair. So in terms of the testing and inspection, we do have a PL and also EL inspection. So for PL inspection, it actually can help us to realize a high efficient inspection. However, the precisionness of the inspection is still problematic. And in terms of EL inspection, because the precisionness is very high. However, if we actually conduct EL inspection for every LED, the efficiency is going to be compromised. And in terms of the repair, when speaking, there are two issues here. So first, if we use the redundant circuit as a design, and then for this redundant circuit, this is going to take a very large proportion of the display area. So in the future, this is going to hinder a kind of a large PPI application. And also a second thing is the large area laser repair. This is also one of the major topics that we are confronting with. And also now the fourth part will be the introduction of BOE, micro LED and mini LED R&D plan, and also our product plan as well. So first of all, BOE is actually a company of making the backlight, back panel as a major technology and fundamental technology. And also BOE actively promote the micro and mini LED technology and product development based on that. And we have three directions. The first is the mini LED backlight. So in this area, we're going to actually use the glass-based mini LED BLU to actually achieve the performance upgrade. And this particular product is going to be actually mass-produced at the mid of this year, 2021. So the dimming zones is larger than 1,000, contrast ratio more than 1 million, and also brightness of larger than 1,000 nits. And the second is the mini LED display. So now is a glass-based PM display to realize the large size seamless splicing display. And this particular product is going to be massively produced in 2021, covering the 7-inch to all size. Pitch can be lower than 0.9. And third direction is the micro LED display. And in this area, together with our backplane technology advantages, we're going to actually respond to the market and coordinate our development and develop as soon as possible. Currently speaking, we are researching on a further advancement of backplane driver technology and integration with the micro LED technology. And also in terms of the backlight of mini LED, the technology core is actually a kind of a low cost glass-based and high brightness and high partition, and also the full size or less splicing, and also high transfer efficiency. And in terms of this particular design, comparing with the PCB backplane, the glass plane can be super thin, and also with a less splicing, and also very low warpage and high stability and reliability. Also, in terms of the driving, we can realizing a ultra high peak brightness of above 1000 nits. And also at the same time, we are introducing the low resistance metal copper technology, realize a local dimming zone of 1000 and also 5000. And also in terms of the mass transfer, we can have over 100 Hertz, 10 times the regular pick and place method, and also the efficiency is 10 times higher, and also the accuracy is very high. And also in terms of the whole process, together with the low cost glass-based advantage, we can really help to reduce the overall product cost. And from 2019 onwards, BOE started to launch all kinds of different mini LED backlight products. In 2019, we had an onboard backlight for automotives with a 12.3 inch. And also on IPC 2020, BOE launched the monitor 27 inch, and also the super large backlight 75 inch for TV. So these backlight products are going to realize over 1000 nits of luminance, and the 75 inch now can actually have 5000 local dimming zones, and the thickness of the module as a whole can reduce 0.9. And in terms of the mini LED display of BOE, we are laser focused on the semicon technologies, seamless splicing with high brightness and flicker free. So by having a super thin design, and also our special arbitrary kind of a splicing technologies, we can actually realize a very kind of a low warpage and high stability and reliability. So this seamless splicing technology has a double-sided process and can realize a kind of a seamless splicing for any sizes. And also micro IC or LTPS or oxide TFT were actually used here to use as a direct driver, and the fine pitch can be realized, which is lower than 1 millimeter. And also in terms of the very last thing, in terms of packaging, we are having the black silicon plus the transparent silicon as the packaging technology. In 2020, we launched the 55-inch kind of a product with the 1.8 pinch, 0.9 pitch, and also the super large 162-inch product. Excuse me. And also in 2020, we actually launched the following mini LED display products. And finally, let me give you a summary. So for mini and micro LED, so this technology has many advantages, and also they do have new applications. And this is actually regarded as the technologies for the future display. But at the same time, it is facing with a lot of challenges, like chip processing, pixel driving circuit, color purity and garment, or mass transfer and inspection, repair, etc. We're still having a lot of challenges to overcome. And finally, we are more than willing to join hands with everybody to really develop the micro LED and mini LED and realize industrialization. So much for my report. Thank you.
Okay, thank you, Mr. Wang, is for keeping the time on time for the whole presentation. So we're open for the questions. I recall there was a question was asked before, and Jose was saying that question can be answered by the BOE. Jose, do you remember which question was?
Yes, we have a question in the past from Heidelberg Instruments, all the way from Heidelberg in Germany. The question was for maskless lithography, for direct laser writing, do you see any applications or any added value in using it for manufacturing micro LEDs?
不好意思，我前面的那个技术，我那个现在不是特别了解。
Sorry, I may not know much about the technology. So you're talking about the laser writing, right?
Yes.
据我了解，激光直写的话，
So
它
for
在
the laser writing, in terms of the panel high precision panel, we have a very good application. But in terms of micro LED, I don't see any application or potential of application of this technology.
Thank you very much. I will make sure that you are introduced to them to discuss potential business. Professor Yang, could you allow me to ask another question?
Sure, go ahead.
I have another question from my side. At the end of the presentation, you mentioned that you want to use black silicon glass. Is there any other challenges for the using of black silicon glass? And is the final price of the product affected?
对，在那个我们最
So
后的黑化的这个方向的
in
话，
terms of the black frame, there are a lot of challenges, of course. If we don't do actually the black,
有一个受一个很大的影响。
the contrast will be compromised. So if we do actually, make the black silicon, it is going to impact the overall
做多厚，然后或者
brightness. So how to make the black layer, and also how thick it should be, and also how do we actually have an overall design, and also the process design. I think that they're having a lot of improvement to the display quality if we do them well, and also the price and cost. We have to consider about the overall cost if we want to promote the product. So in terms of the direction of low cost, the black gel or the kind of a black picture as the major kind of a solution, I think that they can help us to drive down the cost even further.
I agree. Thank you for the great answer.
I think we have a question from Andrew Huber from Instrument System. Mr. Hubers, can you ask your question? Hello?
I believe Mr. Huberts is no longer with Mrs. Huberts, by the way, is no longer with us. But
Okay.
I would like to ask the organizers to promote Chris Scan from Bessie, all the way from Austria. Chris, thank you very much for being with us. What's on your mind?
Thank you, and thank you for the great presentation. In the presentation, you mentioned that your preferred method for die attach is laser transfer. And I wondered if you could comment on what do you see as the advantages, especially relative to other options like pad transfer and other methods.
对对。我认为在优势
So in terms of the advantage, yes. So laser transfer is adopted and also favored. And also we can realize a large area scanning using laser transfer. And for the panel makers, because our glass size are always very big, so from Gen 4 to Gen 10, only the laser transfer technology can help us to realize a super large size plane scanning. And if we directly apply on the TFT panel, laser transfer has a lot of advantages. But for other transfer technologies, I don't want to say that they're bad, but I think not that good in terms of application. And also for laser transfer technology, it also has its unique issues. For example, as for how to actually have a splicing of the back panel, and also some kind of bonding technologies and adhesion technologies, etc. All issues need to be solved.
Thank you.
Okay, let's move on to the next speaker, and it's from Play Nitride. Mr. Falcon Liu. So his talk is development of the micro LED display and the future opportunities.
Hi.
You can start now, yeah.
Yeah, okay. Hi, this is Falcon from Nitride. I'm glad to have this opportunity to share the micro LED display development and future opportunities from Nitride's point of view. So we know now we need a display and especially while this COVID-19 timing. Now displays everywhere, but we need it to connect to people. So not only the like before display is kind of application, but now it is like part of our life. So if we see about the displays history, so it's starting from CRT and now moving to LCD or OLED and even to micro LED. The reason why we need to have new display is very simple. We want a better display, and we want to use the display everywhere, not only in your your personal life, but also in a lot of different applications. Therefore, Nitride already has some achievement about micro LED display technologies. So here, samples what we demonstrated, that is we call it pixel matrix, and this is a tiling display. We have 48 modules tiling together, and you can see from the left-hand side that the one module is very small, and this is a base micro LED. We have a unique technology transfer to the PCB, and then we can easily to tiling a much bigger screen. So here, this example is 48 modules, but of course we can tiling to any bigger or any different shape. And comparing to the right-hand side, this is LCD. We input the same video, and we can easily to see the better contrast and better color, and even it's much brighter. And of course, this we adjust to the LCD's best performance. We're not trying to make it like LCD looks very worse. However, of course, LCD is good enough for our life, but for future, we need a better display. So here you can easily to see the difference from micro LED to LCD. And another case for micro LED is it can be flexible. So we work with AUO in 2020 last year and demonstrate a 9.4-inch flexible micro LED display. And this one, you can see that it can be either convex or concave. So the micro LED display, even the display is micro LED chip itself that is rigid, but it still can be flexible since the micro LED chip is very small. So while you do any flexible bending, you won't bend the micro LED itself. And of course, the micro LED, there will be a very important feature that is to make a transparent display. So in 2019, we worked with Tianma, and that we demonstrate a micro LED transparent display. And this one, we can see that it can see through the display. And of course, the border is very slim, about 0.8 millimeter width. And this very narrow border, there's no any frame required. So there's a lot of applications, especially for automotive industry. They are very interested in this technology. And right-hand side shows another application is 1.25-inch wearable display. And with wearable display, micro LED can help with a very high brightness and good contrast. So therefore, while you have outdoor go for sports, then the micro LED will be very good for you to see under the sunshine. So I think a lot of speakers already introduced micro LED, what is micro LED and what is micro LED display. But here I just found another point to define the micro LED. So the left-hand side, this is a LED chip, and there's including the packaging, the substrate, and also the thin film layer. So if we want to make a micro LED, which is much smaller from the original micro LED packaging, so the first we remove the packaging, and then we remove the substrate layer. So only remaining the AP layer, which thin film layer. So it's about less than 10 micrometer thick. So with this very thin layer, so you have to make it very small. So that's micro LED. And usually people talking about mini LED, that's a thin film layer with the substrate. That's the mini LED case. So the size is kind of this definition, but we think the thickness will be more accurate definition between mini LED and micro LED. So this is one LED chip. And the display that we need to make it an array, or we call a matrix. And the traditional LED chip, you can see that this is very big. So we can make the display, but the pitch will be bigger, be wider. So that means like we only like LED TV need to have a distance, then you can see beautiful thing. Otherwise you get clear, then you see a lot of stuff. So micro LED advantage people are discussing is one perfect thing is that the power could be lower. And also the high brightness is a very important feature of micro LED. And the ultra high resolution, which is capable for AR or HUD applications. But this one, we need to have the micro LED on silicon backplane. And then flexible, what I already showed, it's already proved we can be flexible. And fast response time means the LED chip, the on-off time is very fast. Just like micro LED and LED is the same. It's a nanosecond scale compared to LCD that is a millisecond scale, or OLED that is a micrometer scale. So micro LED on-off time is very fast. And of course, that's an important thing. The micro LED is the same as LED. We have very good reliabilities. So compared to OLED that is organic, there's some constraints there. Micro LED will be good reliabilities, and especially this is a very important feature for automotive applications. So comparing the structures from LCD, OLED, and micro LED to right, we can see micro LED structure is very simple. You just need a driving backplane and a very small micro LED chip on top, then it's done. Comparing to LCD, that's a bulky structure. It's mature. However, the structure is thick. So if we want to go for flexible or anything new or transparent, LCD is unlikely to be the solution. OLED is good, but the organic itself has some challenges. So therefore, they need some of the encapsulations. So get a little bit thicker. It can be flexible, but has some constraints there. And also, if we want use for the transparent display applications from LCD, the structure is bulky, and of course that the color filters matrix is unlikely to be transparent. And OLED, you see some OLED TVs, transparent TV in the market. However, you can find transparent, not very bright. The reason is OLED material itself has for a lifetime. So you need to consider brightness, lifetime, and the transparency. You need to find the balance. So therefore, that's current OLED TV. It's transparent, but not so bright. And micro LED, the chip size is very small. So most of area can be transparent. So we can get high transparency, and also chips itself, we don't have any line concerns. So it's easy to make a high transparency and high brightness transparent display. And that's very important for unique, how can we have high brightness, high transparency, and also excellent reliability display for that's these three features are very important to make a transparent display, especially for automotive industry. So here just shows an future or our target that's for everywhere in your windshield, your side window, your dashboard, your CID, your back mirror, everywhere in the car, they can be used by micro LED technology. So how to realize micro LED display? The first we need we need very small LEDs because that can be the smaller LEDs means it can be lower cost, but the very small LEDs has challenge to need to have very good efficiency, and also this is a display, so we need to have every chip is similar to each other. So these are the targets to make smaller LEDs. And another things, of course, we need to have cheaper mass transfer solutions. And with these two solutions, then if we can solve these two questions, then the micro LED display can be very cheap in the future. So first, for mass transfer, I think a lot of speakers already introduced, and I share you some animations to understand the mass transfer ideas. And this is for based on the stamping process. So we have a backplane, and now we have prepared a wafer and micro LED chip already arranged. Then that can feed to the target panels. And then we have a stamp here and pick up the locations for the backplane. So then we pick up the micro LED chips and to the backplane, and then do pre-assignment on the locations we need to have, and then bonding the micro LED chip on the backplane and move back. So this is a typical cycle for stamping, and this process can be very, very fast. So for plain nitride solution, we use RGB 3 colors. So after red colors, then we do the green colors mass transfer, and then we do the blue colors mass transfer. So after the transfer, if everything's perfect, then we have a perfect screen. However, that's unlikely. Defects are unavoidable. One defect coming from the micro LED chip itself, from wafer, because there's particles, so it's very difficult to have zero particles environment. And another, of course, while you do the mass transfer, there might be some of the defect there. If we count the current conditions, then for a Full HD screen that we have 30,000 bad pixels, and this is unlikely to be repaired because the cost is too high. So we need to have some of the solutions we call like mass transfer. So we need like something for mass repair. And here is the plain nitride solution. So we have the same thing, a wafer arranged, and then the thing different is we have a special stamp, then we can pick up only the chips which matching to the defect locations, and then transfer to the target backplane, and then move back. So you can see here, the defect location, we have additional micro LED chips next to it, and then it can return to the good screen. So after one color, and then we do another color, then that's the repair solution. And here we can see here, people were asking if there's enough space to put a lot of micro LED chips there. then you can see that microchip is very small. So you can easily to put a lot of micro LED chips there. So this idea, there's no any problem. So here's an example. So we do the repair, then it can be become good. If there are any cases, there's something missing, then we can just do pick and place, just because the defect pixel is very limited, and that can save a lot of cost. So from prototype to manufacturing, we do a lot of things: LED size and efficiency improvement, LED wafer defects and uniformities improvement, mass transfer, mass repair, mass inspection, lots of things. The key is the cost. So how can we reduce the cost? That's the key for micro LED to become commercialized to everyone. Okay, so for the very end, just briefly introduce our company. We founded in 2014 and located in Taiwan Hsinchu Science Park. And we already have a production lines producing micro LED chips and display. And we got several awards from different locations. And for Nitride, our core technology is wafer epitaxy, micro LED chip processing, and include from mass transfer, inspection testing, and to mass repair. And the others, we work with our partner, just what I showed before, like with AWO or with Tianma together. And thank you very much for my presentations, and wish everyone can be healthy and use the display to, and this time use the display to connect people with each other. Thank you.
Thank you very much for a great presentation. We have some questions in the room. The first one is coming from WANG, one of the great companies with huge future that we have in Europe. We go to Warsaw and we go to the femtosecond laser company Fluence. Darius Spirat, Czech, could you ask the question you have for Play Nitride?
Hi, nice to meet you, and thank you very much for your presentation. So my question is simple. I know you like to focus on very, very small, but on the first slide, you said about this panels you have, modules, that you have a screen of consisting of 48 modules. And my question is, how many modules can you combine to make it bigger, and what's the limit there?
Well, there's no limit, just depends on the module number. So we can, now our demo is around 37 inch, but then we can have bigger 175. And if we have more modules, 150, 200, anything, or any shape you like. So the tiling, the most beautiful things for tiling is that you can tile to any display size or even aspect ratio based on your requirement, or even said, tell me your living room size, and we can cover all of your walls.
Okay, can I have one more?
Anything for you, that is.
Question, just one more of the pixels. Of 100,000 hours gradation.
Darius, we're having some problem with the connectivity. So if you wouldn't mind writing your question in the chat, Falcon will answer it. The second question is coming from my R&D manager. So let's listen to Ana Gonzalez. Dr. Gonzalez, what's on your mind?
Thank you for giving to me the word, and thank you for the presentation. It was great. Yes, my question was about what is the limitation in order to further reduce the time of analysis and this reparation procedure of your LEDs. This is related to the speed of automation, of the automation tools, or it is more related to technical issues, or in order to reduce and to reduce the cost as well?
Oh, sorry. So may I repeat your question? So you're asking about the process is automatic or non-automatic, and then
what is the limiting factor or making the repair part faster or cheaper? What is the limitation? Is it the speed of the machines?
Well, I think the repair, the best thing is if you can make the transfer perfect, then there's no any repair required. So that's the target. However, if you need to repair, then it depends on the defect counts you have. If like, for example, I indicate if you have 30,000 defects, then that means you need to find something can repair very fast and with a lot of defect repair a lot of defect quantity at the same time. So then, for example, we make some of the mass repair technology. If the defect number is very limited, like 10, 20, then maybe we can use pick and place to repair. So the repair technology really depends on the first pass yield. And the final goal is we need to find the cheaper solutions for repair, because the repair won't make the display to be perfect, but it cannot generate the real production anyway.
I think, Falcon, you gave the answer that Anna was dreaming about. She's going to connect you with companies that will want to help you on this. I would like to go next to Chris from Bessie. Chris, what's on your mind?
Yeah, I think the last answer kind of answered part of my question, but my question is related to the repair process. So it's a very innovative process. I'm just wondering, do you have to dedicate wafers for just the repair process because you're picking selective dye from the wafer, which would render the wafer unusable for a mass transfer process? And then is there a trade-off in terms of yield between this method of repair versus picking individual dye because of the waste of the wafer?
Yes, of course, we can, by this condition, we can 100% to utilize all the wafers, all the chips from wafer. However, the defect pattern will be different. So it's very easy just by some of the algorithms, or we use AI to calculate how can we pick up choose this, where the location to pick up the micro LED chips for repair. And this one, I think we use the one wafer to repair a lot of panels, and that we try to utilize to use most of the LED chips on top.
There are many questions in the chat, but Professor Yang is back with us. Professor Yang, this is your session.
Sorry, my computer has some problem. It just quit me on, so I have to reboot the computer. Okay, so I think we're done for the questions, right?
Yes.
Okay, let's move to the next speaker. We are very honored to have another one is from, I think from Taiwan, right? Oh no, I'm sorry. Okay, we will have Mr. Ding Yuan from Tianma. So he will share his talk, the opportunity and the challenge of the micro LED display for automobile applications. Yes. So Mr. Ding is the director of the R&D in Tianma.
喂，能听到吗？
能听见啊，开始，
喂，可以听到吗？
可以听见，可以听见，
喂，
可以听见，你把你的静音打开。
喂，
能听见你，能听见。
喂，可以听到吗？
可以听见，可以听见，
喂，
可以开始，
能听到吗？
可以开始，能听见。
哎，严博。
可以听见。
哎，我这里为什么听不到声音？
你可能麦克风没有打开。 你是不是静音了？你把你的静音给。在你的左下角有一个这个静音的那个，是不是静音给关掉？可以把这个打开。
喂，
我们能听见。
严波，你能不能挥一挥手？
能听见。
能听到是吧？那我就开始讲了。线上的各位嘉宾，大家好，我是来自天马研究院的丁渊。今天主要跟大家分享的就是 Micro LED 显示在车载领域的机遇和挑战。这个报告呢，主要分为5个部分。那下面我给大家一一介绍一下。那首先，今天报告主要呢集中在 TFT 驱动的 AM 的 Micro LED 显示技术。那么它的显示像素呢，就是由50微米以下的微型的 LED chip 所组成。那么如果是 Full HD 的分辨率的话呢，我们需要通过巨量转移的技术，然后转移600多万颗微型的 LED 芯片到我们的显示面板上。那目前而言，就是从理论上来讲 ，Micro LED 的显示，无论从响应速度、亮度等等。几乎所有的显示性能都是最优的。目前而言，主要就是2个不足吧，一个就是成本，还有一个技术成熟度。那么这2点也是未来 Micro LED 显示技术所要突破的。那么除了显示性能非常优异之外，那 Micro LED 还有一些结构优势，也介绍过，就是一个就是 Micro LED 显示可以实现超高的透明度。那 Micro LED 显示的整个叠层是非常简单，不像 LCD 和 OLED， 其实它们的层数是非常多的，较为复杂。那层数越多，我们知道层数越多，它的透过率就会越低。另外呢 ，Micro LED 凭借它的超高的亮度以及寿命，所以它的发光区域其实可以做得非常小。那进而呢，我们可以得到非常高的一个
as small as possible. So there are lots of big area of transparent area. About 100 ppi. OLED actually can make 20% transparency, but for Micro LED, the transparency can be above 60%. Also, there is another type of advantage, which is borderless. So for LCD, because it needed to actually have a same sides of the frame, and also for OLED, because this is organic, material oriented, so it has to have a certain kind of a special packaging technology and TFE packaging, for example, for flexible. But for Micro LED, as we already stated, that this is also a very good resilient over the very strict requirement of the environment. So it does not need to have a very strict kind of a packaging. And also it can have a seamless splicing, and also can be conducted in a borderless way. We can make a Micro LED as a standardized module so that we can tailor-made to the customer's needs. And just now, I have already said that no matter we are talking about performances, but also in terms of structure, we do have other advantages. So currently speaking, is it possible for us to really have a full deck development in all different kinds of downstream applications? So now in terms of the cost, I don't think that this can be further elaborated or extended to more applications in the short run. And next, let's take a look at the analysis of the cost structure. For OLED and LCD, their cost is proportionally related and corresponded to the display size. But Micro LED has this cost related to resolution. So for example, if for WK like HD, it may need to have 10 million more of the drive or ICs. So actually, that is to say, we're going to have exponential growth for the Micro LED number if the resolution is increased to a very high level. And also, while at the same time, with improving resolution, yield is not going to actually be compromised. But for actually that was for LCD and OLED, but for Micro LED, actually the kind of a yield will be impacted. And also, that resolution, of course, is being improved. Now, talking about TV from 2K, 4K to 8K. And also, we're going to have at least like 100 million Micro LEDs. needed for the large size panel and display. So I think that technology-wise and also application-wise, micro LED is a very difficult technology. So what types of applications are there that are suitable for micro LED first? And now it should have two features. First, we should have, if you want to have a super performance of display, and then you choose micro LED. This is something cannot be achieved by OLED or LCD. And second, not that price sensitive in like kind of a high-end niche market. For example, over 100-inch super large splicing screen. You can use micro LED. And then overall speaking, we have been seeing all the different application fields in display in a consumer electronics area. Talking about cost and technology difficulties, there are a lot of barriers. So those barriers are automotive, transparent display, and splicing display. So we can apply fully the micro LED. And also another one is for wearables. Wearable itself is small in size and also low resolution. So technology barrier is very low. So this is price sensitive area. And second, in terms of power consumption. So we need to solve the consumption. Currently speaking, power consumption for micro LED display is still very high. And for Apple Watch, the latest generation of Apple Watch, it is already using LTPO technology and can have 1 Hz drive. But for micro LED, in order to have 1 Hz drive, it is still difficult in terms of technologies. So when I was introducing to you about the application field, and automotive is one of the major area of application of micro LED. And also, on the other hand, Tianma, as a company, had a lot of breakthroughs and progress in this particular application. And now in the automotive application, we have already realized #1 market share. Every 5 vehicles, there was one vehicle that used the Tianma display. And also automotive display is also one of the strategic directions of Tianma. So in terms of the micro LED application in the future, we are prioritizing, automotive application. On 3 major technology pathways. The first one is transparent display, as I already introduced to you that. And in the future, we can actually make a flexible transparent display. And second part is splicing display. And for splicing display, there are some kind of tech solutions that some inside the vehicle. So with the very good feature of seamless splicing, we can actually realize the tailor-made needs of the drivers. And also, finally, flexible display. And first, flexible micro LED. Comparing with OLED, it has a high flexibility, high brightness, and long lifetime. And comparing with LCD, in terms of HDR, high quality of the picture, LCD is still disadvantageous comparing with micro LED. And then just now, I was already talking to you about the future applications of micro LED. And now what I'm going to tell you is challenge of micro LED. So first, talking about FD drive, AF, micro LED, there are 3 parts. The first is drive IC or display IC, how to make the IC as small as possible. While at the same time, the lighting kind of efficiency can be very high. And also some kind of lightness and also brightness, as well as the color quality, they need to be further improved. And second of all, how to realize a borderless kind of application and also the thermal spray and also thermal stability and also the mass transfer. This is a core technology of the micro LED. How can we transfer as many micro LED as possible in the shortest period of time and also realize 100% yield of transfer? This is something that we have to overcome in specific in the future. And then let's talk to you about some of the challenges that we have been encountering during the application. Let me give you some examples. The first is uniformity. So as you may see here on this slide, so the further away from IC, the darker it is. And also we're going to see some kind of blocks here with very low uniformity because of 3 reasons. The first is the chip itself, the uneven distribution of brightness and also the color. And second is caused by the backplane. The drive current of micro LED is 2 times larger in terms of exponential comparison with LCD. So let's just say why the larger or the further away from LCD, the further away from the display, the darker it is. And also there is a kind of a mass transfer unevenness. So we can actually optimize the drive and also optimize the algorithm, etc., to compensate. I mean, for the backplane. And the third part is for the mass transfer. And also because during the transfer, the pressure of the temperature should be very uniform. So if we can really kind of reduce the difference, we're going to have a very good improvement of the performance and uniformity. The other part is power consumption. The 3 challenges are, first of all, LED efficiency. So the efficiency is lowered if the chip size is smaller. So we have to improve the efficiency. And second is for drive. So TFT itself will consume certain power by itself. And also this is something that we have to solve as a panel maker. We do have certain technology in actually reducing the TFT voltage. And third is drive mode. So in terms of micro LED, comparing with OLED, for OLED, normally it's like the nano ampere kind of a drive, but in a super low current, because of the low efficiency, the brightness or lighting efficiency is very low for micro LED. So we need to have a very good drive under a very dense current. And I'm going to give introduction about this later. And also second, how to reduce the power consumption. Apart from the improvement of the lighting efficiency of the micro LED itself, we could also think about other ways. Let me take a look at the left chart. For OLED, the brightness is the highest. It is between 0 to 70 degrees. The brightness efficiency is the same, in between 0 and 70. So we can have some kind of a design of the backplane structure. On the right, we can have 2 reflection walls design and also 2 reflection layers on the bottom, so that by using efficiently the light to really reduce the power consumption. And next, we're talking about the drive mode, and left chart was something about the PWM kind of a method. And this is still the traditional drive mode of the LED and LCD. And then the kind of a drive current is very high and density is very high. So it can make full play the high brightness of the micro LCD. But actually the resolution itself cannot be optimized. And also on the bottom chart, we're talking about the traditional OLED drive mode, which is using the frequency adjustment to drive the different current. And then that particular drive current is a nanoampere level. So normally there is no way for us to actually make the brightness high for micro LED. And also in the future, we're going to combine PWM with PAM as the hybrid model for the drive. So that is a hybrid mode of PAM plus PWM. And with this particular frequency adjustment, combining with the advantage of these 2, actually this should be the most usable kind of a drive mode for the micro LED chip. There's another challenge, which is about the temperature stability. Under the high temperature, the brightness efficiency of micro LED will be changed, especially the red chip. Under 85 degrees C, it can only have 25% of the performance comparing with the ambient temperature. So if we raise the temperature even higher, the color will be changing all the way to green. So fundamentally, we need to first of all have something to do with the micro LED chip. And for the red chip, we have to make the temperature performance well. And also on the other hand, we can have some temperature compensation to improve.
Just like the right bottom, you could see we could use the blue chips plus the wavelength transformation to achieve the full color. Of course, for the overall transfer, that is beneficial as well. And now let's look at the challenges of transfer. Here on the table, I list 6 mainstream transfer methods. Up till now, the most mature one is still the stamp methods. Most of the prototypes are produced in this way. However, for the stamp, its efficiency and speed are relatively lower. So for the mass production, that is not efficient. As for the future, just like many speakers have mentioned, we are more interested and see confident in the laser transfer, especially for large volume or large size. The laser transfer is still under research, so we need to make further breakthrough. Of course, the yield of transfer is very important. For HD resolution, if the yield is 99.99%, then still there are over 600 defects. Even if you could achieve 99.9999% yield, still there are 7 defects. To repair, of course, it is necessary. But in current stage, especially for the medium to short term, if the yield is not too high, then those reductive repair is more appropriate, just like previous speaker mentioned. As for the future, if the yield could be very high, we still need the single point inspection and repair that will be more efficient and cost-effective. But of course, it's more challenging, so we need to make further breakthrough in the future. And now I'd like to turn to the development progress of Tianma in display in automotive area. One is the transparent display. As other speakers have mentioned, we have the in the world, that is the ultra-transparent 7.56 display. We have won the SID award. And the second product on the show was the flexible display, also around 7.56 inch. We show the head of the robot with 50mm bending radius, and we could reduce the radius further. That is because of our flexible technology. So through the flexible micro LED, we could make breakthrough so that in the future, there could be more applications in the cars to make it more beautiful in design. On the right, also the latest one is the 5.04 spliced display. For the frame, it is less, the border is less than 0.03 millimeter, very, very thin. You could barely see it. And just like you could see from the right, we slice into an abnormal shape with 4 pieces, and we could also piece into a very long display, so that will be very appropriate for the onboard display in the car. And finally, for Tianma, actually in micro LED display, we have had many years of development from the beginning of 2008 till now. And we already transformed from the concept to prototype. And now it shows the micro LED technology is appropriate, and that will be a very promising display technology in the future. But if we want to achieve mass production, but like I said, there are many challenges we need to overcome. So in the future, I hope those from chips, design, equipment, etc. We hope we could work with all of these partners, so together we could make the technology more mature to be mass produced. That is all from me. Thank you.
Okay, thank you, Mr. Jin, for the excellent presentation. And now we're open for the questions. I think, Jose, you have the first question, right?
Well, you know, Professor Yang, I always have questions, but
okay.
You know, my question here is very simple. You at some point to increase the efficiency, you added a reflection layer directly on the top of the substrate. So I'm worried, are there any thermal expansion problems for these 2 layers?
拓展问题吗？是副作用吗？还是什么？
就他说你那个反射层的话，有没有会受到温度？
Do you mean because of the temperature it might be affected? Maybe the temperature would lead to mismatch.
the coefficient of thermal expansion is very different between the reflection layer and the silicon substrate. So I'm wondering if there is a problem.
目前我们验证下来
Up till now, according to our test, it is okay. There is no specific issue that draws attention. But at the high temperature, as you could see, the red reduces sharply. That is the issue.
Thank you.
Okay, we have Ben Lin. Ben Lin from Terraces. You can ask your questions, or I can read your question. Okay, the question was, what will be the mainstream interconnect material between the die and the substrate after mass transfer?
Well, this concerns many technical details that I could not disclose. Sorry.
Okay, Steve, you want to ask the question by yourself? Okay, I think the question was, is there any head-up display application?
Well, up till now, we are negotiating with the OEMs because many auto companies are interested in transparent display. So we are seeing if there is further possibility of development. For others, I cannot disclose. Sorry for that.
Okay, we have one more. It's from Inel Atoning. Is it possible to transfer the color conversion filter over the blue micro LED? In your slide 16.
对，这个现在这个方式我们其实也做出来过。
Well, up till now, we already did that, but still we would use to separate layers and then put them together.
I think we have to move on, and thanks for the speaker again. Okay, so now let's move the next speaker, Chen from Southport.
Hello.
Can you, hey, Mr. Chen, can you share the screen?
Yeah, I'm trying. 我再看一下。Okay. Hello, I want to share my experience about the micro LED mass inspection. Okay, I want to start from a simple problem. Why micro LED is so special? I think it's because the size. When size is getting smaller and smaller, today we have micro LED. Actually, some research groups have announced the idea about nano LED. So smaller size brings us large numbers, and large numbers brings us many possibilities. So it will become great applications. So I think today when we talk about micro LED's applications, I think we are not only talking about display. because maybe we could talk about the lighting, the optical communication, the biomedical applications, or the mass class lithography, or more other applications. Actually, I think the right problem we should ask is not about how good the micro LED TV can be. Actually, in physics, we should ask how to use million programmable light source in a small area. In the history of optics, this is the first chance we have this kind of optical device. So all the difference comes from the size. The smaller size bring us more opportunities and of course more challenges. So what is the challenges in inspection? There are three typical methods used to identify the quality of LED. First, the PL spectrum that can give us the material properties. Second, the EL spectrum. It will give us the device properties and sometimes the information of the contact. And second, the electrical properties, the IV curve, will give us a detail of contact condition. To do this kind of measurement, there are four basic parts for LED inspection. First, the probe. We use the probe to light up the LED. Second, the SMU. We use the SMU to measure the electrical properties. Third, the light source. We use it to excite the PL spectrum. Third, the most important things, we use a photodetector to get the luminance from the micro LED. And when size getting smaller and smaller, what kind of problems will happen? The mini LED actually seems still fine, but when things go to micro LED, the LED size is too small, so the probe cannot probe the LED correctly. So have some works about the submicro and nano probe. But I know some other teams in Taiwan, they try to change their mind. Why not use a backplane to light up the micro LED? And if the backplane can measure the electrical properties at the same time, it will be a great platform for the micro LED inspection. So there are so many talented teams here to working on the probe, working on the electrical measurement. But what about the camera? Actually, in optics, every kind of size variation, it's all about resolution. So what will be the problems when the size getting smaller? When your micro LED gets smaller and smaller, you will find out that the light go to your detector will be mixed. So actually with the small micro LED size, we cannot identify each LED's optical properties. So we need better spatial resolution to do the optical inspection. If we have like 10 micrometer, 5 micrometer, or 1 micrometer micro LED in the future, or in the future nano LED, it's the optical problems. So I want to introduce you the Southport JMAT system. We integrate the PL Raman image and the PL Raman spectrum, and also the TRPL spectrum, and all the EL rate analyzing algorithms with some micron spatial resolution and sub-nanometer wavelength resolution in one system. And this system has been widely used in the 2D material inspection, the perovskite inspection, and also the quantum dot and the quantum technology, the single photon emission inspection. So what can we do for micro LED here? For example, after chip processing, we will have maybe 10 million micro LED on the wafers. In our system, we can get high resolution PL image on whole 4-inch wafer in 10 minutes. At this stage, defects and error rate can be identified. For example, if you zoom in this data, you will see the defect. You will see what area the PL spectrum is not uniform, or what micro LED cannot light up with laser. If you zoom in again, you can see every PL spectrum and every PL image of each micro LED can be measured. If you keep zooming, because our resolution is really good with submicron spatial resolution, so the PL spectrum of each micro LED can be clearly measured. So it's a good news for R&D and future inspection. You can see it's the PL spectrum of each micro LED in the left image. Here's a video of our measurement process. You can see every point in the left image is a spectrum, is a PL spectrum of 1 micro LED. So you can easily identify the defects here. And if you really want to know the detail, really want why it's bad in spectrum, every micro LED spectrum has been really recorded. So you will have a whole database of every micro LED on your wafer. So what's more, we cooperate with Jasper Display. They have a great CMOS backplane for micro LED driver. We use their driver to light up to micro LED. So of course we can get the PL and EL spectral mapping easily of each micro LED. Also, we can get zoom in and get the detail of each micro LED spectrum, EL spectrum. And with the great digital modulation technology, Jasper Display's backplane can easily measure the whole current mapping of the whole micro LEDs on this panel. And of course, you can select whatever the pixel on the panel, and you can find out the IV curve of that pixel. So actually, with this kind of setup, if you are interested in the mini display application, we can provide you a total solution for inspection in your R&D stage and also for your mass production stage. So what's more, I want to emphasize one thing, that the wavelengths, because if we claim that micro LED is the best display we will ever have, we need to cheat the human eye. But human eye is a really great color sensor. For some young guys, 2 nanometer wavelength difference will be recognized. So in our system, we have sub-nanometer wavelength resolution in our PL and EL spectrum. So what's more in Southport, I want to introduce you some in-house technologies. We have micro 3D imaging for 3D AOI, it's good for the ITO process. And for the future micro LED or nano LED tendency, we already have the super resolution PL and PL image spectrum. So actually, we are waiting for the burst of nano LED and over the 1 micrometer micro LED here. And third, I know there are so many laser treatment process in the micro LED production process. Actually, we can provide one thing we say digital optics. We have programmable multi-photon system, which is a better and new way to control the laser spot, the multiple laser spots in a real-time and programmable way. So this is the typical micro LED production process. with our material analysis system, we can do the PL, EL, and the optical inspection you want. With our micro 3D module, you can do the inspection on the ITO film or the surface morphology after etching process. With the laser, with our multi-pulse system, we can provide a better way to control your laser spot for the laser lift up and laser trimming process. So let's make a brief summary here. Why inspection is so important? I think it's about time to market. I think everyone here is waiting for the time to market of micro LED. But in my opinion, better inspection tool will bring us faster design of experiment cycle. And faster DOE cycle will shorten the time to market. Actually, I think the best way to shorten the time to market is identifying things as clear as possible in your R&D house. So if you have the better inspection tool to make everything clear, and you can have a better inspection tool also brings you stable production process. So what are the challenges we have in mass inspection? I think it's all about size, because the smaller LED size brings large numbers of LEDs. So the throughput, the efficiency is very, very important. And the smaller size also require better resolution in optics. So with the smaller size, we need better resolution and better efficiency. So actually we need different tools and concepts to identify the quality of LED. So what kind of solution do we have? With Southport system, we can provide you the PL and EL measurement with micro LED, even smaller than 40 or 10 micrometer. And with our partner JDC SpecLane, we can give you the PL, EL, and the IV curve measurement for micro LED on the panel. And that's my presentation. Thank you.
Okay, thank you. So it's an excellent talk to touch the issue about the inspection and evaluation. It's always the very important issue for the micro LED. So we have a question from Vincent Calvo from Comptek. Okay.
Yes, hello, hi. Yeah, I have a couple of questions. So the first one was about the laser spot size that you use to measure these micro LEDs. How small is the spot size? And another question was that you mentioned that you can do also single photon counting and flint measurements through the wafer. How long it takes to make a full wafer inspection with those techniques? And also related to that, we know that, for instance, the single photon counting or carrier lifetime measurements in micro LED depends a lot on which spot or which location of the micro LED actually is being measured, either in the center of the micro LED or in the edge. There will be variations of these measurements. So how can you ensure repeatability on those? Thank you.
Okay. About the light spot size, in our system, it depends on the objective lens you use. Typically, we can go to like 1 micrometer or smaller. And you talk about the TCS, PC, and flint. Actually, I have not used the flint to measure micro LED before, but the flint is a fast measurement if you don't need so many pixels. And I think what is the laser spot, what is the location of the laser spot on the single micro LED. Actually, because our resolution is smaller than the micro LED, so actually you can choose. In our standard production, we put the laser spot exactly on the middle of the micro LED, because we already have the PL image, so it's easy to get the right location.
Vincent, are you happy with the answer?
Hi, yes, okay. Yeah, sorry, we were in mute. We were discussing here.
Okay.
Okay,
Okay.
yeah, thank you. Thanks for the answers, yes. Yeah, okay.
Okay, Jose, it's your turn now.
Thank you very much, Professor Yang. I loved this presentation. I love having a Raman system integrator in the room. It's a dream for the semicon inspection. I would like to ask, is there any idea to integrate Raman with other inspection technologies like OCT, optical coherence tomography, or perhaps hyperspectral imaging?
Actually, we already integrate the Raman to confocal and also in hyperspectral image. But in hyperspectral images, the measurement will longer time. So if you are talking about the Raman on micro LED, actually Raman is a photon-photon interaction. So I think the small defect on your material, inside your material, is it important for future micro LED application? Is it important? I think Raman will play a interesting role in this kind of inspection.
I hope so. I'm a huge fan of this technology, and I love what you are doing, integrating Raman for semicon inspection. Congratulations.
Thank you. Thank you.
Hey, IGN, it's very nice talk, and I have one question. For the EL measurement, is it EL measurement has to be like to be connect to the contact to the drivers, or in order to light up, or do you have any other way to inspect the wafers? You know, like finish the wafers, and you can do the EL test without using the electronics to control electronics?
Actually, Southport do the optical part, but in with our partner, the JDC's backplane, you need to bound your micro LED on the backplane. And I know so many different kind of technologies about narrow probe or nanoprobe array. They try to attack this problem. But when micro LED like goes to 5 micrometer, or I say 2 micrometer, the pad is too small. So I still not see the general solution here in the market.
Okay, so we might have the solution, so maybe we can discuss later.
Thank you.
Okay, we have to move on. It's a very excellent talk, and we need to thank the IGN again. And now we move on to the last speaker of our session. It's Junko Liang, Dr. Junko Liang from Comptek.
Hello. Can you, by the way, unmute my video? For some reason, it says that the host has unmuted my video, but can you hear me? Okay.
Yes, we can hear you.
Yeah.
All right, very good. So hello, everybody. Can you see my screen?
Crystal clear.
Oh, very good. My name is, greetings from Finland. I'm the CTO of Comptek Solutions. Very happy to be here to present our company and also to discuss about the exciting world of micro LEDs. So today we are going to talk about the desperate need to passivate the compound semiconductors. And like we have heard today, so there is for some mysterious reasons that when you decrease the chip size, that you lose a lot of efficiency in micro LEDs, and we have a solution for that, and we're going to talk about that during this talk. Here's, by the way, nice picture of micro LED sidewall. If you haven't seen it, it's a high resolution electron microscope picture. This is how the micro LED looks in when you look very closely. So briefly who we are. So we are a fairly young company located in Southwest Finland, Turku, where we have our own labs and clean room processing and characterization tools. We consider ourselves as forerunners in III-V surface engineering with the top expertise in passivation, III-V material passivation. And I think this is becoming very crucial skill nowadays, since many different application areas require a very good performing III-V devices like micro LEDs, like we will see today. And Comptek, we are essentially a process provider from whom our customers can have a tailored processes for their application or device, which basically means that we can adapt our processes or technology based on the customer materials and overall process flow. And here are some highlights of our capabilities. So basically, we have developed our own tools to apply our technology. And here is one snapshot, which basically is an ultra-high snapshot of one of our reactors, which is a ultra-high vacuum reactor connected with the clean room and inert gas environment. So with this kind of equipment, we can do very customized processes and for our customers, and also doing that under a very controlled environment, which is actually required for the micro LED type of devices. And as you might know, in a semiconductor business, many time phenomena, which basically determines your device performance, are happening, and that's why we are also doing the characterization from atomic level to the device level. And we have also our own tool to some of those like level micro LED characterization. Previous talk was very interesting also which highlights basically the need for doing proper inspection. So here on the bottom left corner is this kind of fluorescence lifetime imaging picture from a micro LED showing how the carrier lifetime is distributed in the LED, for instance. And on the right hand side there is a lifetime. We can see, for instance, how the carrier lifetime is changed in a quantum versus the barrier layers, for instance. So these are very important methods for us to evaluate our processes and also to understand what is really happening at the material and device level. So to the topic, challenges related. So today we have heard we have had a discussion about the mass transfer, those kind of things, which seems to be already solved in like X-Celeprint was showing very nice performance in the mass transfer quality. But there are other things like how to do bonding, etc. properly. But one of the most important factors when you decrease the chip size is actually the sidewall quality. So like we heard, the efficiency goes down drastically when you decrease the chip size, and that is actually because of the defects at the sidewall. And those basically play a very important role in determining the ultimate performance of and the efficiency of micro LED. So what is happening at the micro LED sidewall? So basically, when you define your LED, you of course do etching by dry processes like ICP. You generate some amount of defects to the sidewall already. But then when you remove that wafer, for instance, from the processing tool, you actually oxidize those surfaces. And 3-5 materials, which the micro LEDs are made of, are very aggressively oxidized. And here is one very nice picture. It is atomic resolution picture from the sidewall of the micro LED, showing this kind of blurry region, and that is a native oxide at the surface, and it doesn't have any good order, or it's like amorphous structure, and this kind of lack of atomic level coordination creates high density of defect states in the band gap of the semiconductor, which is shown in the top right corner image. And these kind of defects, they act as a non-radiative recombination centers, which means that when you inject you would like to have a light out of the LED, that the carriers you inject are actually lost in these defects and generating heat, but not light. So you don't have your efficiency goes down drastically. And that is also shown here in a real life picture, how if you have 100 micron micro LED and you go down to 5 micron, your efficiency goes down drastically, but also the current density where we achieve the peak efficiency goes to the very high current densities. So this is big issue and needs to be solved before if you want to make very high brightness and efficient displays or any kind of micro LED application. And here at Comptek, we have a solution for that, so which we call Controx. It is by this Controx process, which I'm going to talk about next slide, is we can achieve up to 98% reduction in the defect state densities compared to existing methods in 3-5 materials. So what is Controx? So basically, it's a family of patented processes for different kind of compound semiconductor materials, where we can transform the surfaces of 3-5s into crystalline oxides, which are with a very low defect state densities and which are stable. So these structures are stable under air exposure or ALD process or against high temperature annealing. So here are some pictures. On the left hand side, there is picture of a native oxide on top of 3-5 semiconductor. It looks this kind of rough and amorphous, and after our process we can create at atomic level very ordered crystalline oxide with the good properties. And this is applicable to many compound semiconductor materials, which here is a snapshot of the material scope that we are dealing with. So of course, here we are mostly interested in the LED and optoelectronic applications, but I need to emphasize that this issue is very relevant in many other fields, which require very high efficiency and good performing 3-5 devices like radio frequency or power electronic transistor applications. So we are active in these areas very much. So what we can do for micro LEDs? So we have a process ready for gallium nitride based blue and green devices, but also a native red color device, which is indium gallium aluminum phosphide. And normally how we do this is like I said, there is might be some existing damage to the processes done by the ICP. So we do preparation step where we heal the semiconductor, like reveal the fresh semiconductor by our methods, and then we do our magic passivation step in a very controlled environment where we can achieve very good chip efficiencies. And after that, so we are not replacing any overcoating process in a sense. So we are just complementary process. So after that, you can do ALD or PECVD coating if required, or depending on your overall process flow. And this, of course, need to be adapted to the particular customer process flow or materials. And for instance, such in a laser application, our process comes in a very final step. We passivate laser facets, but in micro LEDs, it can come in a various points depending on the overall process flow. So some results. So the native red color is very challenging to be done efficiently in very small sizes. That is because of the high surface recombination rate of the indium gallium aluminum phosphide material, which is the native red color, and mainly because of aluminum, which is easily generates this kind of high defective layers. And here we demonstrate, like in material level, there is we can clean this material. We can get very nice electron diffraction pattern showing clean surface, and doing our process on top of that, we basically change the symmetry of the surface and create crystalline oxide. So it works in the material level, and then applying this process to the meso level, we see very nice improvement in a carrier lifetime, which basically means that you reduce the non-radiative recombination rate a lot. And yet, when you apply this to the chip level in micro LED, you see big enhancement in the efficiency of the device. And yet, more examples. So, like I said, the size dependency of the efficiency is very big issue, and so this left-hand side graph shows you the relative efficiency versus state-of-the-art 80 micron micro LED. So you see that normally when you decrease from 80 micron to 5 micron, you have like only 30% of the efficiency normally. But when we do our process, we see big improvements. So it's only basically the size dependency of the efficiency is reduced a lot. And same goes with the current density. So the current density basically is reduced a lot because of the efficient passivation. So to summarize a little bit the added value, also to answer the EPI question, what we can do for you. So with our atomic level passivation technology, we see that we can greatly enhance the efficiency of micro LEDs, which basically translates into brighter and less power consuming devices. And we also think that our technology is the key enabler for red color in native RGB displays. So you don't need to use necessarily the down conversion from gallium nitride to the red color. And also, since our process is basically removing defects, we also increase the manufacturing yield, so there will be less non-uniformity in the chips. Actually, like that we saw in the previous slides, that I can go actually back one back, so you can see that the performance distribution of the micro LED is also reduced by our process. And yeah, so how we collaborate? So what you can do for us, I would say that join us and collaborate with us to enable this next micro LED revolution. So basically how we work is that we do the process optimization and implementation to the customer, and then the customer gets access to our IP portfolio, and we do the technology transfer, and we have a partnership with well-known equipment maker Reber, who can provide mass production tools to apply our technology for micro LEDs. So thank you. I think I was on time almost. Happy to answer your questions.
Okay, thank you.
I think we have some sound problem with Professor Yang at the moment.
Okay.
I think it's related to the fact that he may have an iPad and a computer connected both to the Zoom channel, because there is some echo. In the meantime, I'm going to take the first question from Comptek Solution. What an amazing added value. We had a question, we had a presentation before you from the company Southport, and I think there is some room for cooperation here. Juncheng from Southport, do you spot here something that we can do together? I will tell him what we discuss in private, but maybe Chen from Southport, you can ask. Yes.
Yeah. Actually, I'm really excited about the great work about Comptek, and I think because you are already working on the defect or molecular scale, so maybe Raman could be an interesting tool to identify the quality about your great work.
Yes, definitely. I see Raman a very interesting tool also to gain more understanding what is happening in the micro LED level. So yeah, very eager to discuss with you more about this.
Yeah, okay. Yeah, we can keep in touch. I think it's a really interesting problem here.
Yeah, I have a question. Can you hear me?
Yes.
Okay. It's excellent talk, actually. It's we always know that the red is always the challenge for us, especially for how to recover the efficiency loss at a small size. And for the gallium nitride, and we have some way to passivate, improvement.
Yeah.
But the red is always the challenge. I think you give a very nice result, and which is very encouraging.
Our process is happening in an ultra high vacuum environment, so it's a little bit exotic process. It's not the PCVD, so we don't deposit anything, but we actually transform the surfaces of 3-5 materials into crystalline oxide, and this happens in a high vacuum conditions. That is why, for instance, Riber, which is a well-known high vacuum process tool manufacturer, is our partner. So they are doing, for instance, the epitaxy, mass production epitaxy equipment for radio frequency applications. So yeah, it's not typical. It's not PECVD. We do it much better conditions than PECVD, for instance.
Okay, so the speed is always a concerning for this kind of the solutions. Yeah. Okay. Okay. So maybe can find some better way to improve that. Yeah.
Yeah. Now I need to say there that the time to process this is comparable with the other deposition techniques such as ALD, for instance. So it's not that. If you do multi-wafer process, you can process many wafers, and the process is conformal and suitable for big wafer sizes like 200 millimeters, where the micro LED is going to gallium nitride or silicon. So we can do that on a big wafers also.
Great. Yeah. So actually, the ALD has some potential, although the ALD is slow. But there is a new technology on the horizon, and it could make ALD faster. So that might be able to do the mass production solutions.
Yeah, there we are. I see in terms of ALD, we are kind of complementary process. So we make a perfect interface between the semiconductor and ALD. Because if you do only ALD, you will have still a bad quality interface between those two materials, and we can passivate that interface because our layers are very thin. So only few monolayers to nanometers. So it's not it's a very thin layer, but it's key is the actual interface between the semiconductor and the for instance ALD coating.
Okay. Okay, thank you.
Thank you.
Any other
Professor
questions?
Yang, we are very out of time, but there is a person in the room, Alexandre from Alos Semiconductor, who is a manufacturer of gallium nitride over silicon substrates. I would like to know his views about this technology and how can it help semiconductor manufacturing companies. Alexander, are you with us? Alexander
yes, I am.
Yes.
Good afternoon, good morning to everybody. Very pleased to be here again. Yes, I also know the Comptek solution, and I think it's a great step forward to solve this issue of inefficiency reduction for some chips. Curious also to see how that will impact red nitride LEDs, which more and more people are looking at. And I also very much appreciate that this is available for larger wafer diameters, because we see that 200 millimeter and 300 millimeter are on the way, in particular to address the yield challenge simply by using style equipment to have very high micro LEDs. Down to even less than 1 by 1 micrometer is the size which we see at some of our customers.
In this event, we have companies, Natis, we have companies like Epistar, we have companies. I want to speak to you, Jouko, from Comptek Solutions. I'm really amazed. I really am. Back to Yang, Professor Yang.
Thanks.
Okay, so if we don't have further questions, and I would like to conclude the whole event, and thanks every speakers all delivered a very excellent talk, and also the whole session we have a broad coverage about the micro LED issues, from manufacturing issues, from aging, or and from the chip side, chip issues, and also a lot of excellent talk from the manufacturing side, especially those challenges they are facing, and also some of the applications. So it's a very good spectrum of the micro LED discussion in this event. So I really appreciate everybody's contributions, and thanks again. And also we had a very nice attendees. I saw that during the peak time, maybe over 150 or maybe more attendees. And also we have excellent discussion after each talks. So again, and it's my honor to chair these sessions, and also bring everyone together for this wonderful event. And also this is a good opportunity to bring everyone together, especially those manufacturer makers and technology providers in Europe, and the manufacturer and technology advances in China and Taiwan. So it's a great event. And again, thanks everyone. Yeah. Okay, so Jose, you want to make some comments? And also,
yes, one quick comment, which is that you see this slide. I want all of you to have it, to remember today. These are the companies who registered today. These are the companies who registered today. You know what we have to do now? We have to make sure that we do business. So all of you right now in the chat, you got a link. You got a link from wonder.me. What you have to do is click on that link. Click on that link and you will appear in an interface for us to connect and do business, for us to connect and make new friends. So please, even if you only have 5 minutes, it is totally worth it. Try it. Click on the link. You will not regret it. You will appear in another interface in which we are going to be using it to connect. I love connecting. This was a fantastic event. Professor Yang, I love co-chairing the meeting with you. It was truly an honor. And I also love all the amazing feedback that I have been receiving during the event from many companies who found potential partners, suppliers, and customers. That's the amazing job that ISA and PIDA, together with EPIC, we have to do. Thank you so much, Professor Jan, from my side. Until the next time, goodbye. See you in wonder.me.
Okay, thanks you, Carlos. Also, thank you, Joe, Jose, and also thank our secretary for ISA and Mr. Chao. So I think we work together and make this event happen. Thanks, everyone. Yeah.